At the heart of our Milky Way galaxy, shrouded behind a veil of dust and billions of stars, lies a mystery that has captivated astronomers for centuries: Sagittarius A. This isn't just any celestial object. It's a supermassive black hole possessing the mass of millions of suns, yet invisible to the naked eye. For decades, this enigmatic entity remained hidden, its presence only subtly hinted at through the gravitational dance of nearby stars. The sheer density of the galactic center, a region known as the galactic bulge, created a formidable obstacle for early astronomers. Imagine trying to study a single grain of sand buried deep within a massive, densely packed sand dune. That's the challenge astronomers faced in discerning Sagittarius A from the overwhelming brightness and chaos of its surroundings. The light from distant stars, struggling to penetrate the thick clouds of interstellar dust, was scattered and absorbed, creating a blurred and confusing view, obscuring the true nature of the galactic core. This wasn't merely a matter of technological limitation. The very structure of our galaxy conspired to hide its heart. Early attempts to chart the Milky Way's structure, even by skilled astronomers like William Herschel, using star counts, were fundamentally hindered by this cosmic curtain of dust. The true nature of the galactic center remained elusive, a dark secret veiled within the brightest region of our night sky. The journey to unveil Sagittarius A would require innovative techniques and a shift in perspective, moving beyond the limitations of visible light to reveal the unseen forces shaping our galaxy. This shift began with the dawn of radio astronomy. In the 1930s, Carl Jansky, an engineer at Bell Telephone Laboratories, stumbled upon a persistent source of radio waves emanating from the direction of Sagittarius. This accidental discovery, initially intended to improve long-distance radio communication, opened a new window into the universe, revealing a celestial realm invisible to our eyes. While Jansky's findings didn't immediately revolutionize astronomy, they planted a seed that would blossom into a new field of study. Groto Reber, a radio engineer and amateur astronomer, built upon Jansky's work, constructing a radio telescope in his backyard and independently confirming the existence of this powerful radio source. This marked the beginning of a sustained effort to understand the mysterious heart of our galaxy, gradually refining instruments and techniques to peer through the cosmic dust. Subsequent decades witnessed the development of progressively more sensitive radio telescopes, revealing a rich tapestry of radio emissions from the galactic center, hinting at the presence of something truly extraordinary hidden within. The emergence of infrared astronomy provided another crucial breakthrough. The infrared astronomical satellite IRIS, and later the Spitzer Space Telescope, offered unprecedented views of the galactic bulge, revealing clusters of stars previously obscured by interstellar dust. These infrared eyes allowed astronomers to start mapping the true shape and extent of the galactic core, while radio telescopes continued to gather data on the intense radio waves pouring from its heart. Together, these observational techniques began to paint a picture of a dense, dynamic region, harboring a mass far beyond what could be accounted for by visible stars alone. The stage was set for the next chapter in this long quest, tracking the precise movements of stars to reveal the invisible force governing their intricate dance. The galactic center isn't merely distant, it's actively concealed behind a formidable obstacle, the galactic bulge. Imagine a bustling city, its skyscrapers so densely packed that you can barely make out the buildings on the far side. That's analogous to the challenge posed by the bulge, a vast spheroidal structure composed of hundreds of billions of stars, gas and dust. This isn't a simple layer of dust. It's a complex three-dimensional region where stars are packed far more tightly than in the flatter disk of the Milky Way's spiral arms. This dense concentration creates an almost impenetrable barrier to observation, scattering and absorbing light before it can reach our telescopes. Visible light, the kind our eyes readily detect, struggles to penetrate this cosmic thicket. The countless stars within the bulge overlap, blending their light into a dazzling but ultimately confusing glow. This makes it incredibly difficult to isolate individual objects within the dense mass, like trying to pick out individual fireflies in a swarm on a moonless night. This inherent opacity presented a major hurdle for early astronomers. For centuries, the galactic center remained a mysterious void, essentially invisible to the most sophisticated tools available, a stark testament to the immense challenges in studying our galaxy's most densely populated region. Early efforts to map the galaxy's structure were significantly hampered by this obstruction, leading to incomplete and often inaccurate models of the Milky Way. Only by developing new observational techniques, moving beyond the limitations of visible light, could astronomers begin to pierce this stellar veil and unravel the secrets hidden within the galactic bulge. This limitation wasn't simply a matter of insufficient telescope power. The very nature of visible light, easily scattered and absorbed by interstellar dust, played a critical role. The dust particles, tiny bits of carbon, ice, and rock, effectively block the passage of visible light, creating dark lanes and obscuring the view of the galactic center. These dust clouds are not uniformly distributed. They clump together in complex patterns, further complicating the already challenging task of observation. Even with powerful telescopes, the image of the galactic center remained a confusing jumble of light and dark, a frustratingly incomplete picture of what lay at the heart of our galaxy. The solution, as it turned out, lay not just in building more powerful telescopes, but in employing different types of light. Radio waves, with their longer wavelengths, prove less susceptible to scattering by interstellar dust, offering a way to penetrate the obscuring clouds and reveal the hidden structures within. Similarly, infrared light, with its longer wavelengths than visible light, offers another avenue for observation. The development of sensitive infrared detectors and telescopes opened a new era in galactic astronomy, allowing astronomers to peer through the dust and observe stars and gas clouds previously hidden from view. The use of both radio and infrared astronomy, combined with increasingly sophisticated data analysis techniques, was instrumental in eventually resolving the mystery at the galactic center, demonstrating that innovative strategies and a willingness to look beyond the limitations of traditional methods were crucial to unlocking the secrets hidden within the galactic bulge. Long before the advent of sophisticated space telescopes and radio astronomy, astronomers attempted to chart the Milky Way using the most basic tool available, their eyes aided by increasingly powerful optical telescopes. These early efforts, however, faced an unexpected and significant hurdle: interstellar dust. Imagine trying to map a city's streets while shrouded in a thick fog. That's the challenge these pioneering astronomers encountered. Interstellar dust, composed of microscopic particles of carbon, ice, and rock, pervades the space between stars, effectively obscuring the view of distant objects. This dust isn't evenly distributed. It clumps together in vast opaque clouds, creating dark lanes that cut across the brilliant tapestry of stars. Early astronomers, lacking an understanding of this pervasive dust, often misinterpreted the variations in starlight intensity as reflecting the uneven distribution of stars within the galaxy. Their maps, based primarily on visible light observations, revealed a galaxy far less structured and symmetrical than we now understand it to be, leading to inaccurate representations of our galactic home. William Herschel, for example, in his ambitious attempt to map the Milky Way, using star counts, unwittingly charted a galaxy significantly distorted by the presence of this interstellar dust, creating an incomplete and ultimately misleading image. The dust wasn't merely an inconvenience. It was a fundamental obstacle to understanding the true structure of the galaxy, its spiral arms, its central bulge, and the hidden entity at its very core. Only by venturing into other wavelengths of light, utilizing radio and infrared telescopes, Could astronomers eventually overcome this significant obstacle and begin to assemble a more accurate and complete map of the Milky Way? This limitation wasn't simply a matter of technological inadequacy. The very nature of visible light itself played a crucial role. Visible light, while essential for our own vision and early astronomical observations, is easily scattered and absorbed by interstellar dust. The longer wavelengths of radio waves and infrared light, however, are far less affected by this dust, allowing astronomers to penetrate the obscuring clouds and glimpse the structures lying beyond. This crucial realization fundamentally altered the course of galactic astronomy. The development of radio telescopes capable of detecting these longer wavelengths marked a turning point, revealing details previously hidden from view. Similarly, the development of infrared astronomy, with its ability to detect the heat signatures of stars and gas clouds, provided a complementary approach, further enhancing our ability to map the Milky Way's structure. These advancements, coupled with improved data analysis techniques, eventually allowed astronomers to build a more accurate and comprehensive model of our galaxy, a model that incorporated the previously hidden structures and revealed the true complexity of the Milky Way, including the remarkable object at its very heart. The story of Sagittarius A's discovery isn't one of meticulous planning, but of serendipity, a fortunate accident that would revolutionize our understanding of the galactic center. In the 1930s, Carl Jansky, working at Bell Telephone Laboratories in New Jersey, was tasked with a seemingly mundane problem identifying sources of static interfering with transatlantic radio communications. His solution involved building a unique rotating antenna, sometimes nicknamed a merry-go-round, designed to pinpoint these sources of interference. What Jansky found, however, was far more profound than mere static. He detected a persistent signal, a consistent hum, emanating from a specific point in the sky, a signal that didn't match any known terrestrial sources. Initially, he suspected the sun, but careful observation revealed a crucial detail. The signal arrived approximately 4 minutes earlier each day, a discrepancy that perfectly matched the Earth's rotation relative to the stars. This extraordinary finding pointed to an extraterrestrial origin, a source of radio waves located far beyond our solar system. Further analysis pinpointed the signal's source to the constellation Sagittarius, a region already known for its intense brightness in visible light, but whose inner workings were largely hidden from view. Jansky's discovery, published in 1933, marked the beginning of radio astronomy, a new field that would prove crucial to unraveling the mysteries of the galactic center. While Jansky himself didn't continue this space-based research, his work provided the foundation for future discoveries, demonstrating that the universe held secrets detectable not through visible light, but through the electromagnetic whispers of radio waves. The path to understanding Sagittarius A had officially begun. This path, however, was far from straightforward. The initial detection was a mere hint, a faint signal amidst a sea of cosmic noise. It would take decades of further research, technological advancements, and the dedicated efforts of many scientists to fully understand its implications. The next significant step came from Groto Reber, who, inspired by Jansky's work, independently confirmed the existence of the radio source and began mapping its properties. Reber, using a larger and more sensitive radio telescope, meticulously scanned the sky, confirming Jansky's findings and providing the first detailed radio maps of the region. His work highlighted the strength and consistency of the signal, originating from a remarkably compact area within the constellation Sagittarius, a signal that could not be explained by any known type of ordinary star. This strongly suggested that something extraordinary, something far more massive and energetic than any previously observed celestial object, was hidden within the dust and stars of the galactic center. The radio emissions, while invisible to our eyes, carried a profound message. The universe was teeming with phenomena far beyond the reach of traditional optical astronomy. The way was now open for more advanced techniques to refine the signal, reveal more of its characteristics, and eventually to definitively identify the source of this potent and enigmatic emission. While Carl Jansky's discovery of radio waves from space was groundbreaking, it was Groto Reber who took the next crucial step: independent confirmation and the creation of early radio maps of the galactic center. Inspired by Jansky's work, Reber, a radio engineer and amateur astronomer, embarked on his own investigation. Unlike Jansky's relatively rudimentary equipment, Reber constructed a more advanced radio telescope in his backyard, a significant undertaking showcasing his dedication and ingenuity. This larger, more sensitive instrument allowed him to not only confirm Jansky's findings, but to also significantly improve upon them. Reber's telescope, a parabolic dish approximately 9 meters across, systematically scanned the sky, meticulously mapping the intensity of radio waves from different directions. His resulting maps provided the first detailed picture of the radio sky, highlighting a region of exceptionally strong emissions in the direction of Sagittarius. The precision of Reber's work, accomplished with relatively limited resources, was remarkable, confirming the existence of a powerful localized radio source deep within our galaxy, a source that demanded further investigation. These early maps, though crude by today's standards, provided essential data that shaped the subsequent decades of research on the galactic center, confirming the existence of a previously unseen source of energy and prompting further exploration using ever more advanced technologies. Reber's meticulous work transformed a serendipitous discovery into a tangible target for future scientific investigation, paving the way for deeper insights into the heart of our Milky Way. The intensity and compactness of the radio emissions as mapped by Reber suggested something far more substantial than a mere cluster of stars. This intriguing characteristic fueled further research, driving the development of larger, more sophisticated radio telescopes capable of resolving finer details within the galactic center. The improved resolution offered by these new instruments revealed a more complex picture, highlighting the intense energy output concentrated in a remarkably small region, solidifying the mystery surrounding this previously unseen source. Reber's work, though conducted with relatively simple technology, laid the crucial groundwork for future discoveries, providing concrete evidence of a powerful and unusual source at the heart of our galaxy. His meticulous maps acted as a roadmap for subsequent generations of astronomers, guiding the search for a definitive explanation for this mysterious radio emission, emanating from the densely packed stars and gas clouds at the center of the Milky Way. The story of Sagittarius A, therefore, is inextricably linked to the innovative spirit of these early pioneers, whose efforts laid the foundation for our current, much more comprehensive understanding of this remarkable and enigmatic object. The confirmation of a powerful radio source at the galactic center spurred a rapid expansion of radio astronomy, transforming our ability to study the previously hidden depths of the Milky Way. Following Reber's pioneering work, scientists across the globe began constructing larger and more sensitive radio telescopes, instruments capable of detecting fainter signals and resolving finer details. This wasn't merely a quantitative improvement, it was a qualitative leap, opening a new window into the universe and revealing phenomena previously undetectable with optical telescopes. Imagine switching from a blurry, low-resolution image to a high-definition view. That's the transformation radio astronomy brought to the study of the galactic center. The increased sensitivity allowed astronomers to detect subtler variations in radio emissions, mapping the complex structure of gas clouds and other celestial objects hidden within the galactic bulge. Techniques like very long baseline interferometry, VBI, which combined data from multiple geographically separated radio telescopes to achieve significantly higher resolution, were pivotal in resolving the ever more intricate details of this region. These technological advancements allowed scientists to pinpoint the location of the radio source with increasing accuracy, narrowing down the possible explanations for its origin. The consistent intensity and compactness of the radio emissions strongly suggested a remarkably massive, yet unseen object at the very heart of the Milky Way, fueling speculation about what this mysterious energy source could be, a speculation that would soon lead to a revolutionary paradigm shift in our understanding of the galactic center. The rise of radio astronomy wasn't just about technological improvement. It was a fundamental change in how we see the universe, moving beyond the limitations of visible light and revealing an unseen world of energy and structure. This shift in perspective, from relying solely on visible light to embracing the broader electromagnetic spectrum, proved crucial in unraveling the secrets of the galactic center. The increased resolution and sensitivity offered by advanced radio telescopes allowed astronomers to not only pinpoint the location of the radio source, but also to study its variations over time, revealing a dynamic and complex environment. These observations, combined with data from other wavelengths like infrared and X-ray, built a compelling case for the existence of a supermassive black hole at the heart of the Milky Way. The radio waves weren't just a byproduct of some unknown process. They were a vital clue pointing towards a region of extreme gravity and immense energy, a region where the very fabric of space-time is warped and distorted. The story of Sagittarius A is thus inextricably linked to the remarkable progress made in radio astronomy, a testament to the power of scientific innovation in expanding our understanding of the universe and the hidden wonders within our own galaxy. The development of increasingly sophisticated instruments, coupled with innovative observational techniques, would eventually lead to a visual confirmation of this long-suspected supermassive black hole. But it was the rise of radio astronomy that first provided the crucial clues leading us on this extraordinary journey of discovery. As radio astronomy matured, the focus sharpened on the intense radio emissions originating from the constellation Sagittarius. No longer a mere whisper of static, this signal emerged as a dominant feature of the galactic center, a powerful and persistent beacon in the radio wavelengths. Astronomers, using increasingly sophisticated instruments, began to characterize this source, assigning it the name Sagittarius A, reflecting its location and its prominence in the radio spectrum. This wasn't a diffuse emission. The radio waves were concentrated in a remarkably compact region, suggesting an exceptionally dense and energetic source at the very heart of the Milky Way. Imagine a lighthouse, its beam cutting through the darkness. Sagittarius A functioned similarly, its radio emissions piercing the obscuring clouds of interstellar dust. The intensity of these emissions, far exceeding what would be expected from any known collection of stars, implied the presence of an object of immense power, an object unlike anything previously observed. Further analysis revealed not only the source's strength, but also its variability. The intensity of the radio emissions fluctuated over time, suggesting a dynamic and active environment at its core. This was more than a passive signal. It was a window into a region of extreme physical processes, a region that hinted at a celestial entity of extraordinary mass and energy deeply hidden within our galaxy. The identification of Sagittarius A as a powerful and variable radio source marked a significant turning point, transforming this intriguing mystery into a compelling scientific problem, demanding a detailed explanation, an explanation that would ultimately revolutionize our understanding of the galactic center. This explanation, as it turned out, would involve one of the most fascinating and extreme objects in the universe, a supermassive black hole. The sheer power of the radio emissions, combined with the source's remarkably small size, strongly suggested an object possessing an immense gravitational pull an object capable of trapping even light itself. While the evidence was still circumstantial at this stage, the characteristics of Sagittarius A pointed towards a scenario far beyond the realm of ordinary stars and nebulae. The variability in the radio emissions further supported this hypothesis, hinting at a dynamic environment where matter is being relentlessly drawn towards an incredibly dense and powerful central object. The stage was set for more precise measurements and advanced techniques to confirm this extraordinary conjecture, a conjecture that would soon be confirmed through meticulous observations of the movements of stars orbiting this unseen powerhouse at the heart of the Milky Way. The discovery of Sagittarius A as a potent radio source thus served as a pivotal clue, guiding the scientific community towards a revolutionary understanding of the galactic center, an understanding that continues to shape our view of the universe. The intense radio emissions from Sagittarius A, while intriguing, were only part of the puzzle. Further observations using a combination of radio and infrared telescopes revealed something even more remarkable. The stars orbiting the galactic center were moving far too fast. Imagine a carousel spinning at an incredible speed. The stars near Sagittarius A were behaving similarly, whizzing around a central point at velocities far exceeding what could be explained by the visible matter alone. These observations, painstakingly made by astronomers over many years, pointed to a hidden source of immense gravitational pull, a force powerful enough to accelerate stars to such incredible speeds. The data collected through meticulous tracking of stellar movements revealed that the stars were not orbiting empty space. They were responding to the gravitational influence of an unseen mass, a mass many times greater than anything visible in that region. This unseen mass was far too compact to be a dispersed cloud of gas or a cluster of stars. It had to be something extraordinarily dense and concentrated, a powerful gravitational anchor holding the entire region in its thrall. The more precise the measurements became, the stronger the evidence grew for an invisible supermassive object at the heart of the Milky Way, an object that could not be seen directly, but whose presence was clearly felt through its overwhelming gravitational influence. This realization transformed the investigation from a search for a radio source into a deeper mystery, the identification of an invisible giant, a powerful celestial force whose existence was revealed only through the subtle yet profound movements of the stars. This invisible giant, it turned out, was far more than a mere curiosity. It was a key to understanding the structure and evolution of our galaxy. The immense gravitational pull exerted by this unseen mass was shaping the orbits of stars, influencing the distribution of gas and dust, and ultimately playing a significant role in the dynamics of the entire galactic center. The mystery, however, was far from solved. The question remained, what was this unseen mass? The existing observations strongly suggested an object of enormous mass confined to an incredibly small volume of space, a scenario that pointed compellingly towards a black hole, a celestial entity so dense that not even light can escape its gravitational pull. While a black hole remained the most plausible explanation, other possibilities, however improbable, could not be entirely ruled out. The discovery of this massive unseen object therefore deepened the mystery at the heart of the Milky Way, fueling even greater scientific curiosity and inspiring the development of more advanced observational techniques to definitively identify this unseen giant and unravel its secrets. This unseen mass became the focus of intense scientific investigation, a quest that would ultimately lead to the most definitive answer, yet the creation of the first ever image of a black hole. While radio astronomy offered a crucial window into the galactic center, penetrating the obscuring dust clouds, it provided only an indirect view. To truly understand the dynamics of the region, astronomers needed to observe the stars themselves. This, however, required a way to see through the interstellar dust that had plagued optical observations for centuries. The solution lay in infrared astronomy, a field that would revolutionize our understanding of the galactic center. Imagine trying to see through fog. Visible light is largely blocked, but infrared, which detects heat, can penetrate more effectively. Similarly, infrared radiation, with its longer wavelengths, is less susceptible to scattering and absorption by dust particles, enabling astronomers to observe celestial objects hidden behind interstellar clouds. The development of advanced infrared detectors and telescopes marked a critical turning point. The infrared astronomical satellite IRIS, and later the Spitzer Space Telescope, provided unprecedented sensitivity and resolution, allowing astronomers to detect and map the infrared emissions from stars and gas clouds within the galactic bulge. These infrared observations revealed a teeming population of stars previously hidden from view, providing crucial data on the mass and distribution of matter in the galactic center. This was more than just a confirmation of existing theories. It opened up a new realm of observation, allowing astronomers to observe details previously hidden behind a cosmic veil of dust. By combining infrared data with observations from radio telescopes, a significantly more complete and detailed picture of the galactic center began to emerge, a picture that would solidify the case for the existence of a supermassive black hole at the heart of our Milky Way. This clearer picture wasn't just a matter of improved resolution. It revealed the intricate dynamics of the galactic core, highlighting the incredibly fast movements of stars orbiting an unseen central mass. The infrared data, combined with precise measurements from radio telescopes, provided compelling evidence for a previously unsuspected concentration of mass at the galactic center, a mass far greater than could be accounted for by the visible stars alone. This evidence strongly supported the hypothesis of a supermassive black hole, an object so dense that its gravitational pull could account for the observed stellar velocities. The infrared observations, therefore, were pivotal in shifting the focus from a general mystery surrounding the galactic center to a specific and increasingly well-defined scientific problem identifying the precise nature and properties of this extraordinarily massive and invisible object. The infrared breakthrough was more than just a technological advancement. It was a fundamental shift in our understanding of the Milky Way, paving the way for the next crucial steps in confirming the existence of a supermassive black hole at its very heart. Ground-based infrared telescopes, while offering significant improvements over purely optical observations, still faced limitations imposed by Earth's atmosphere. Our planet's atmosphere absorbs certain infrared wavelengths, reducing the clarity and completeness of the data. To overcome this, astronomers turned to space-based infrared telescopes, instruments positioned above the atmospheric interference, offering a vastly improved perspective. The infrared astronomical satellite IRIS, launched in 1983 by NASA, was a pioneering mission providing the first all-sky infrared survey. While not specifically focused on the galactic center, IRIS demonstrated the immense potential of space-based infrared astronomy, revealing previously hidden structures across the cosmos. Imagine removing a layer of fog to reveal a hidden landscape. That's the transformative effect IRAS had on our view of the universe. The data collected by IRAS, though limited by its technology, highlighted the abundance of infrared sources throughout the galaxy, emphasizing the need for more sensitive and focused observations. This need led to the development of subsequent missions, most notably the Spitzer Space Telescope, launched in 2003. Spitzer, with its advanced instruments and ability to operate at longer infrared wavelengths, significantly enhanced our ability to observe the galactic center. Its highly sensitive detectors, cooled to extremely low temperatures, allowed it to pick up faint heat signatures from across the galaxy, providing a far clearer view of the stars and dust clouds surrounding Sagittarius A. Spitzer's long-term observations provided crucial data on the distribution and movement of stars near the galactic center, significantly strengthening the case for a supermassive black hole. The combined data from IRS and Spitzer, therefore, were instrumental in painting a far more detailed and accurate picture of our galaxy's core, providing critical evidence in the ongoing quest to understand Sagittarius A. These space-based infrared observations were not just confirmations of ground-based findings. They provided a far more complete and nuanced view, free from the distortions and limitations imposed by Earth's atmosphere. The data revealed subtle details in the distribution of stars and gas, highlighting the complex dynamics of the galactic center and further strengthening the evidence for a supermassive black hole at its heart. The infrared observations also played a crucial role in identifying regions of star formation and other energetic processes hidden within the dust clouds, giving astronomers a more complete understanding of the environment surrounding Sagittarius A. By combining these space-based infrared observations with data from other telescopes and observational techniques, scientists built a compelling case for the existence of a supermassive black hole at the center of our galaxy, setting the stage for even more precise measurements and ultimately the creation of the first direct image of this enigmatic object. While infrared observations revealed the hidden stars within the galactic bulge, it was the meticulous tracking of these stars' movements that provided the most compelling evidence for a supermassive black hole at the Milky Way's center. This groundbreaking work, largely spearheaded by Reinhard Genzel and Andrea Ghez, involved years of painstaking observations pushing the limits of both observational technology and data analysis. Imagine watching a swarm of bees. Their individual movements appear chaotic, but careful observation reveals a complex, organized dance around a central hive. Similarly, Genzel and Gez's teams meticulously tracked the motion of individual stars orbiting the galactic center, a process requiring extraordinary precision and patience. Using powerful ground-based telescopes equipped with adaptive optics to compensate for atmospheric distortion, they followed the paths of these stars over many years, measuring their positions with astonishing accuracy. This involved working in the infrared wavelengths, piercing the obscuring dust clouds, and capturing images of stars far closer to the galactic center than ever before. The data they collected revealed a stunning pattern of stars moving at incredibly high speeds, their orbits strongly suggesting the presence of an unseen, immensely massive object at the very heart of the Milky Way. The precision of these measurements was remarkable, allowing scientists to calculate the mass of this unseen object with a high degree of certainty. This wasn't a simple calculation. It involved detailed modeling of the star's orbits, accounting for the complex gravitational interactions within the densely packed galactic center. The results independently obtained by Genzel's team at the Max Planck Institute and Gez's team at UCLA were striking. The unseen object possessed a mass millions of times greater than our Sun, concentrated in a region smaller than our solar system, conclusive evidence of a supermassive black hole. This pioneering research, representing a remarkable feat of observational astronomy and data analysis, provided the most direct and compelling evidence yet for the existence of a supermassive black hole at the heart of our galaxy, a discovery that would transform our understanding of the Milky Way and the universe beyond. Genzel and Gez's work not only confirmed the presence of a supermassive black hole, but also provided crucial insights into its properties. The precise measurements of stellar orbits allowed scientists to estimate the black hole's mass with unprecedented accuracy, refining our understanding of these enigmatic celestial objects. Their research also highlighted the dynamic nature of the galactic center, revealing a complex interplay of gravitational forces shaping the movements of stars and gas clouds. This pioneering work, recognized with the 2020 Nobel Prize in Physics, stands as a testament to the power of long-term, meticulous observation and advanced data analysis in unraveling the universe's most profound mysteries. The data obtained by Genzel and Gez's teams were instrumental in shifting the scientific consensus, moving beyond mere speculation to provide strong quantitative evidence supporting the existence of a supermassive black hole at the center of our galaxy, a finding that continues to shape our understanding of galactic evolution and the universe's largest-scale structures. Their work laid the crucial groundwork for the next major breakthrough, the creation of the first-ever image of a black hole's event horizon. Among the many stars orbiting the galactic center, one stands out: S2. This star, a relatively bright and massive object, follows an exceptionally tight and fast orbit around Sagittarius, bringing it remarkably close to the suspected black hole. Imagine a tiny marble whizzing around a bowling ball. That's somewhat analogous to the S2 star's rapid orbit around Sagittarius A. The extremely close approach of S2 to the central object provided astronomers with an unparalleled opportunity to study the effects of extreme gravity. By precisely tracking S2's orbit over many years using advanced infrared telescopes and sophisticated adaptive optics to compensate for atmospheric distortions, researchers were able to extract remarkably precise data on the star's velocity and trajectory. This precise tracking, carried out by teams led by Reinhard Genzel and Andrea G. Zied, was crucial. The data revealed that S2 was responding to an incredibly strong gravitational force, far greater than could be accounted for by the visible matter in the vicinity. The precise shape and timing of S2's orbit, a highly elliptical path, provided the most robust constraints yet on the mass of the central object. Using the laws of gravity, astronomers were able to calculate the mass required to generate the observed orbital characteristics of S2. The results were astounding. The calculations pointed to a mass millions of times that of our Sun, densely packed into a region smaller than our own solar system, powerful evidence for a supermassive black hole. The S2 star's orbit, therefore, wasn't just a celestial dance. It was a critical piece of evidence providing a direct and quantifiable measure of the immense gravitational pull emanating from Sagittarius, solidifying the case for a supermassive black hole at the heart of our galaxy. This wasn't simply a confirmation of existing theories. The precise data obtained from S2's orbit allowed scientists to test the predictions of Einstein's theory of general relativity in the extreme gravitational environment near a supermassive black hole. The observed effects on S2's orbit, such as gravitational redshift and subtle shifts in its trajectory, were consistent with Einstein's predictions, providing further compelling evidence for the existence and nature of Sagittarius A. The study of S2's orbit therefore stands as a remarkable example of how precise astronomical observations can be used to not only confirm the presence of previously unseen celestial objects, but also to test fundamental theories of physics under extreme conditions. The data provided by S2's orbital characteristics were pivotal in building a compelling scientific case for the existence of a supermassive black hole at the center of our Milky Way galaxy, a case that has been further strengthened by subsequent observations and ultimately culminated in the creation of the first-ever direct image of this remarkable celestial object. The precise tracking of stellar orbits near the galactic center, particularly the meticulous observations of the S2 star, provided astronomers with the data necessary to calculate the mass of the unseen object at the heart of the Milky Way. This wasn't a simple calculation. It involved sophisticated modeling accounting for the complex gravitational interactions within the densely packed region. Imagine trying to predict the motion of a single billiard ball amidst a chaotic game that's analogous to the complexity of modeling stellar orbits near Sagittarius A. The teams led by Reinhard Genzel and Andrea G. Zied utilized sophisticated computer simulations incorporating Einstein's theory of general relativity to account for the extreme gravitational effects near the central object. The models considered the gravitational pull not only of the central mass, but also of the numerous stars and gas clouds within the immediate vicinity, creating a highly intricate and dynamic system. By comparing these models to the precisely measured orbits of stars, especially the highly elliptical orbit of S2, scientists were able to constrain the mass of the central object. The results were stunning. The calculations revealed an unseen mass equivalent to several million times the mass of our Sun, concentrated in a volume smaller than our solar system, a density far beyond anything encountered in ordinary stars. This wasn't just a confirmation. The quantitative precision of the mass determination achieved through these detailed calculations offered compelling evidence pointing towards only one explanation: a supermassive black hole. This incredibly high mass densely packed into such a small space could only be explained by an object possessing the immense gravity of a black hole, a conclusion that solidified the existence of a previously unseen celestial giant at the center of our galaxy. The determination of Sagittarius A's mass therefore stands as a remarkable scientific achievement, highlighting the power of precise observation and sophisticated modeling in unveiling the universe's most profound mysteries. This mass determination wasn't merely a theoretical exercise. It had profound implications for our understanding of galactic evolution and the role of supermassive black holes in shaping the structure of galaxies. The calculated mass far exceeding that of any known stellar mass black hole firmly established Sagittarius A as a supermassive black hole, a type of black hole believed to reside at the center of most large galaxies. The precise measurement of its mass provided critical data for testing models of black hole formation and growth, refining our understanding of these enigmatic objects and their influence on their surrounding environments. This precise determination of Sagittarius A's mass therefore was more than just a number. It was a landmark achievement providing compelling evidence for the existence of supermassive black holes and paving the way for further investigations into their properties and their crucial role in the evolution of galaxies. The precision of this measurement also allowed for further tests of Einstein's theory of general relativity under extreme conditions, showing a remarkable agreement between theory and observation in one of the universe's most extreme environments. This success not only solidified the understanding of Sagittarius A, but also set the stage for future advancements in our quest to image and understand black holes, underscoring the vital role of precise observation and data analysis in unlocking the secrets of the cosmos. The convergence of evidence from various observational techniques, radio astronomy, infrared astronomy, and the meticulous tracking of stellar orbits finally led to a conclusive answer to the mystery at the heart of the Milky Way. Sagittarius A is a supermassive black hole. This wasn't a sudden revelation. It was the culmination of decades of research, technological innovation, and the tireless efforts of countless scientists. The immense mass calculated from the precise measurements of stellar orbits by Reinhard Genzel and Andrea G. Zeid's teams far exceeded the combined mass of all visible stars in the immediate vicinity. This discrepancy, combined with the intense radio emissions and infrared signatures observed, could only be explained by an object of extraordinary density, an object possessing the immense gravity of a black hole. Imagine a cosmic drain relentlessly pulling in matter and energy that's analogous to the effect of a supermassive black hole at the center of a galaxy. The sheer scale of Sagittarius A's mass, millions of times that of our Sun, firmly placed it in the category of supermassive black holes, objects now understood to reside at the centers of most large galaxies. This wasn't merely a confirmation of a theoretical possibility. It represented a fundamental shift in our understanding of the Milky Way and its evolution. The existence of a supermassive black hole at the galactic center fundamentally altered our view of galactic dynamics, influencing our models of star formation, gas distribution, and the overall structure of our galaxy. The confirmation of Sagittarius A as a supermassive black hole therefore stands as a landmark achievement in astronomy, marking a profound leap in our understanding of the universe and the forces shaping the cosmos. The next challenge, however, was equally daunting, capturing a direct image of this invisible giant. This quest to visualize the invisible would require a revolutionary approach, pushing the boundaries of observational astronomy and technological innovation. The success of this endeavor, the creation of the first image of a supermassive black hole, would not only provide a visual confirmation of this long-suspected entity, but also open a new era in our understanding of black holes and their profound influence on the universe. The confirmation of Sagittarius A as a supermassive black hole thus marked a pivotal moment, shifting the focus from indirect evidence and theoretical models to the exciting possibility of directly observing this enigmatic object, a possibility that would soon become a reality. Black holes, those enigmatic regions of space-time where gravity reigns supreme, aren't all created equal. They come in a remarkable range of sizes, each with its own unique characteristics and formation mechanisms. Imagine a collection of pebbles, rocks, and boulders that's analogous to the diversity of black holes. At the smaller end of the spectrum are stellar mass black holes, typically ranging from a few to tens of solar masses. These fascinating objects form from the dramatic collapse of massive stars at the end of their lives, often marked by spectacular supernova explosions. When a star several times heavier than our Sun exhausts its nuclear fuel, its core implodes under its own gravity, resulting in the creation of a stellar mass black hole. A step up in scale are intermediate mass black holes, ranging from hundreds to thousands of solar masses. Their formation is less well understood, with theories suggesting they might arise from the merger of multiple stellar mass black holes within dense star clusters, or through the steady accretion of matter over vast timescales. Then there are the true titans, supermassive black holes such as Sagittarius, weighing millions or even billions of solar masses. These behemoths, residing at the centers of most large galaxies, likely formed through a combination of processes, perhaps starting with the collapse of enormous gas clouds in the early universe, or through the merging of smaller black holes over cosmic time. Beyond even these giants are the hypothetical primordial black holes theoretically formed in the extreme conditions of the early universe shortly after the Big Bang. These might range in size from tiny asteroid-sized objects to potentially much larger ones, their existence still largely unconfirmed. Finally, at the extreme upper end are the ultramassive black holes weighing in at over 10 billion solar masses, true cosmic leviathans residing at the hearts of exceptionally large galaxies. Understanding the different types of black holes, their formation mechanisms, and their diverse properties is crucial to unraveling the mysteries of galactic evolution and the vast dynamic universe we inhabit. The classification of black holes by mass and formation mechanisms, therefore, is more than just a taxonomic exercise. It provides a critical framework for understanding their role in the universe's grand scheme. Sagittarius A, with its millions of solar masses, firmly belongs to the supermassive category, but its relatively low activity compared to other supermassive black holes presents a fascinating puzzle. The study of Sagittarius A, therefore, is not merely about understanding a single black hole. It's about gaining a deeper understanding of the entire spectrum of these cosmic giants and their diverse behaviors, an understanding that will undoubtedly continue to evolve as our observational capabilities and theoretical models advance. This diversity, from the relatively small stellar mass black holes born from dying stars, to the gargantuan supermassive black holes shaping entire galaxies, highlights the remarkable range and complexity of black hole phenomena in the universe, underscoring the richness and ongoing mystery of this remarkable class of celestial objects. While Sagittarius A's confirmation as a supermassive black hole was a monumental achievement, it's crucial to understand its place within the broader context of these cosmic giants. Its mass, estimated at around 4 million times that of our Sun, is significant, but it's far from the largest supermassive black hole ever observed. Imagine comparing a large boulder to a mountain. Both are massive, but their scales differ dramatically. Similarly, while Sagittarius A is a supermassive black hole, its size is relatively modest when compared to some of the absolute behemoths found at the centers of other galaxies. The black hole at the center of the galaxy M87, for instance, boasts a mass billions of times that of our Sun, a staggering difference in scale. This variation in mass has profound implications for their respective environments and behavior. Many supermassive black holes are far more active than Sagittarius A, relentlessly consuming surrounding matter and emitting powerful jets of energy across vast cosmic distances. Sagittarius A, in contrast, is currently relatively quiet, showing periods of low-level activity punctuated by occasional bursts or flares. This difference in activity may be partly due to the availability of material. The Milky Way's central region is currently less dense than the environment around some more active supermassive black holes. However, the reasons for these differences are still actively being investigated. Comparing Sagittarius A to other known supermassive black holes therefore highlights the diversity within this class of celestial objects. The differences in mass activity levels and surrounding environments emphasize the complexity of black hole physics and the need for further research to fully understand these intriguing cosmic entities and their role in galactic evolution. Sagittarius A, while remarkable in its own right, is ultimately one piece of a larger puzzle, one that helps us contextualize the remarkable scale and diversity of supermassive black holes across the universe. By studying Sagittarius A in detail, and by comparing its properties to those of other supermassive black holes, we can refine our understanding of black hole physics, their formation mechanisms, and their profound influence on the evolution of galaxies. The relatively quiet nature of Sagittarius A, while initially seeming less spectacular than its more active counterparts, provides a unique opportunity to study the fundamental properties of a supermassive black hole without the interference of intense radiative emissions and powerful jets. This comparative approach, combining observations of Sagittarius A with those of other supermassive black holes, ultimately allows for a more robust and complete understanding of these fascinating objects, their diverse behaviors, and their pivotal role in the universe's grand design. The name Sagittarius A, while seemingly straightforward, holds a fascinating history and reveals much about the evolution of astronomical nomenclature. The Sagittarius part simply reflects the object's location in the sky within the constellation Sagittarius. This is a common practice in astronomy. Many celestial objects are named according to their apparent position within a constellation. The A designation, however, is more specific. In the early days of radio astronomy, when multiple sources were discovered within the Sagittarius region, astronomers adopted a simple naming convention. The first detected source was labeled A, the second B, and so on. Therefore, Sagittarius A represents the first significant radio source discovered within that constellation. The asterisk appended to the name, however, is unique. Astronomer Bruce Ballack and Robert Brown, using high-resolution radio imaging in the early 1970s, identified a particularly compact and intense point source within the larger Sagittarius A complex. To distinguish this remarkable object, they added the asterisk borrowing from a convention used in atomic physics, where an asterisk sometimes denotes an excited state, a higher energy configuration. While not a formal astronomical naming rule, the asterisk served as a clear marker indicating that Sagittarius A was more concentrated, more energetic, and ultimately more mysterious than the other radio sources in its vicinity. This informal designation, however, proved remarkably effective, quickly becoming the standard nomenclature used worldwide. The name Sagittarius A, therefore, is more than just a label. It's a testament to both a historical naming convention and a recognition of the object's unique importance and its initially enigmatic nature, a name that perfectly encapsulates the long scientific journey towards understanding the supermassive black hole at the heart of our Milky Way. The asterisk, often spoken aloud as star, ironically sits at the end of the name of an object that isn't a star at all, but rather a black hole, an object that doesn't emit its own light, but instead bends space-time and absorbs everything that ventures too close. This seemingly simple name, therefore, encapsulates the complex journey of discovery, reflecting the evolution of astronomical understanding and the ongoing quest to unravel the universe's most profound mysteries. The name Sagittarius A, with its blend of convention and subtle implication, serves as a lasting reminder of the scientific detective work involved in uncovering the secrets of our galaxy's heart. The discovery of a supermassive black hole at the heart of our Milky Way, while remarkable, is not an isolated phenomenon. Astronomical observations have revealed that supermassive black holes are remarkably common, residing at the centers of most, if not all, large galaxies. Imagine a universe where nearly every large city has a hidden, powerful engine driving its growth and evolution. That's somewhat analogous to the prevalence of supermassive black holes. This wasn't always apparent. Early galaxy observations, hampered by limited technology and the obscuring effects of interstellar dust, often failed to reveal these hidden behemoths. However, as observational techniques improved, particularly with the advent of radio astronomy and infrared astronomy, the evidence for the presence of supermassive black holes at galactic centers mounted. The observation of unusually bright galactic cores regions known as active galactic nuclei provided early hints suggesting the presence of incredibly energetic processes powered by immense gravitational forces. These active galactic nuclei, often emitting vast quantities of radiation, are now understood to be powered by supermassive black holes actively consuming surrounding matter. The identification of these energetic sources across a vast range of galaxies strongly suggested a universal pattern, a supermassive black hole acting as a gravitational anchor and engine at the center of most large galaxies. The discovery of supermassive black holes at the centers of galaxies therefore wasn't merely a confirmation of a theoretical prediction. It revealed a fundamental feature of the universe's largest-scale structure, suggesting a deep connection between the formation and evolution of galaxies and their central supermassive black holes. This ubiquity, in turn, underscores the importance of understanding these cosmic giants and their profound influence on the cosmos. This realization has spurred intense research into the formation and evolution of both supermassive black holes and their host galaxies, leading to numerous hypotheses regarding their intertwined histories. The sheer prevalence of these cosmic behemoths highlights their pivotal role in shaping the universe's structure, underscoring the importance of continuing to study these enigmatic objects and their profound impact on the cosmos. The discovery of Sagittarius A as a supermassive black hole therefore wasn't just a local finding. It provided a crucial piece of a much larger puzzle, demonstrating that these powerful entities are not isolated anomalies, but rather a fundamental component of galactic structure across the universe. The near-universal presence of supermassive black holes at the centers of galaxies raises a fundamental question. Why, while we've amassed substantial evidence confirming their existence and characterizing their properties, the question of their origin and prevalence remains one of the most compelling mysteries in astrophysics? Imagine discovering that nearly every city on Earth has a hidden, powerful engine beneath it. That's the scale of the enigma posed by supermassive black holes. Several hypotheses attempt to explain their formation, but none yet provide a completely satisfactory answer. One leading theory suggests that supermassive black holes formed early in the universe, perhaps from the direct collapse of enormous gas clouds, clouds far larger than any seen today. These massive clouds, under the influence of their own gravity, might have collapsed directly into black holes, providing the seeds for the supermassive behemoths we observe today. Another theory proposes that the first stars vastly larger than any that exist now lived short, violent lives and collapsed directly into black holes, forming the seeds from which supermassive black holes grew through accretion and mergers. A third hypothesis suggests that supermassive black holes grew through a combination of accretion and mergers of smaller black holes over cosmic timescales. Smaller black holes formed from the collapse of individual massive stars might have gradually merged, gradually accumulating mass and growing into the supermassive objects we see at the centers of galaxies. Each of these scenarios, however, raises its own set of questions, highlighting the complexity of these processes and the need for further research to determine which, if any, offers the most complete and accurate explanation. The question of why supermassive black holes exist at the centers of most galaxies therefore remains a central focus of astronomical research, a puzzle that continues to drive our exploration of the universe and its most fundamental structures. The answer will likely involve a complex interplay of factors, a challenge that will require a convergence of further observational data, sophisticated theoretical modeling, and a continued spirit of scientific curiosity. This enduring mystery underscores the vastness of the unknown and the ongoing quest to understand the universe's most fundamental building blocks. The existence of supermassive black holes at the heart of nearly every large galaxy challenges our current models of galaxy formation and evolution, prompting us to continually refine our understanding of these cosmic behemoths and their pivotal role in the universe's grand design. The quest to answer this fundamental question, therefore, is a testament to the ongoing nature of scientific inquiry and our relentless pursuit of knowledge about the cosmos. The question of how supermassive black holes form remains a significant challenge in astrophysics, with several competing theoretical frameworks vying for acceptance. These frameworks attempt to explain how these colossal objects, weighing millions or even billions of times the mass of our Sun, could have arisen in the relatively short time frame of the universe's history. Imagine building a skyscraper in a few hours. That's the scale of the challenge in explaining the rapid growth of supermassive black holes. One prominent theory posits that supermassive black holes formed early in the universe, perhaps from the direct collapse of enormous gas clouds. These clouds, far larger than any seen today, might have collapsed directly into black holes without forming individual stars, providing the seeds for the supermassive black holes we observe today. This direct collapse scenario requires specific conditions such as a low-density environment and a relatively high abundance of dark matter. But if these conditions were met in the early universe, it could have resulted in the formation of supermassive black holes with relatively little time. Another leading theory proposes a more gradual process: the growth of black holes through accretion and mergers. Smaller black holes formed from the collapse of individual massive stars could have subsequently merged, gradually accumulating mass over billions of years, eventually forming the supermassive black holes we observe at the centers of galaxies. This hierarchical growth model suggests a complex interplay of processes, including the accretion of gas and dust, as well as mergers with other black holes gradually building up the mass of the central black hole. A third, more speculative hypothesis involves primordial black holes. These hypothetical objects, potentially formed in the extreme conditions of the early universe, might have provided seeds for supermassive black holes, subsequently growing through accretion. Each of these theoretical frameworks offers a unique perspective on the formation of supermassive black holes, and ongoing research combining observational data with increasingly sophisticated simulations is crucial in determining which, if any, of these models most accurately reflects the complex reality. The quest to understand supermassive black hole formation, therefore, is an ongoing scientific endeavor highlighting the interplay between theoretical models and observational data in our quest to unravel the universe's mysteries. The relationship between supermassive black holes and their host galaxies is far from coincidental. Observations reveal a remarkable correlation between the mass of a galaxy's central black hole and the mass of its bulge, the dense spheroidal central region of stars. Imagine a tree. Its trunk's size is often related to the size of its branches. Similarly, the mass of a galaxy's central black hole seems to be intrinsically linked to the mass of its bulge. This correlation, observed across a wide range of galaxies, suggests an intimate connection in their formation and evolution. While the precise mechanisms aren't fully understood, several hypotheses attempt to explain this intriguing link. One prominent theory suggests that the black hole and the bulge formed together, perhaps from the same initial collapse of a massive gas cloud. The central region of the cloud, collapsing more rapidly under its own gravity, might have formed the black hole while the surrounding material coalesced into the bulge. In this scenario, the black hole and the bulge would grow simultaneously, maintaining a consistent mass ratio. Another theory proposes a more dynamic interaction, where the black hole's growth influences the bulge's formation and vice versa. A rapidly growing black hole could release enormous amounts of energy, potentially driving outflows that limit star formation within the bulge. Conversely, a higher rate of star formation in the bulge might provide more material for the black hole to accrete, fueling its growth. This intricate interplay suggests a feedback loop where the black hole's activity influences the bulge's development, and the bulge's mass in turn affects the black hole's growth. Regardless of the exact mechanisms, the strong correlation between black hole mass and bulge mass highlights a fundamental connection between these two crucial components of galaxies. This observed relationship therefore provides crucial insights into galactic evolution and the complex interplay of forces shaping the structure of galaxies across the universe. The exploration of this relationship is a continuing area of research, promising to further illuminate the intricate dance between black holes and the galaxies they inhabit. Further research into this correlation will likely shed more light on the processes that shaped the galaxies we observe today. The relationship between the central black hole and the galactic bulge, therefore, is not merely a statistical observation. It represents a fundamental aspect of galactic evolution, hinting at a deep and dynamic interplay between these two key components. This close connection further underscores the importance of studying supermassive black holes to gain a more complete understanding of the formation and development of galaxies across the universe. While supermassive black holes are often associated with intense energy output and dramatic celestial displays, Sagittarius A presents a fascinating exception. Unlike many of its counterparts, which power blazing quasars and active galactic nuclei, Sagittarius A is relatively quiet, exhibiting a surprisingly low level of activity. Imagine comparing a roaring bonfire to a gently glowing ember. Both produce heat and light, but their intensities differ dramatically. Similarly, while Sagittarius A possesses the mass of millions of suns, its current energy output is far less than many other supermassive black holes. This relative quietness isn't necessarily indicative of a dormant or inactive black hole. Rather, it suggests a unique phase in its evolution or a distinctive interaction with its surrounding environment. Astronomers have detected occasional flares, sudden bursts of radiation from Sagittarius A, hinting at episodic feeding events where small amounts of matter are captured by the black hole's immense gravitational pull. However, these events are infrequent and relatively weak compared to the continuous intense radiation emitted by many other active supermassive black holes. The reasons behind Sagittarius A's relatively low activity are still being investigated, but several hypotheses exist. One suggests that the relatively low density of gas and dust in the Milky Way's central region limits the amount of material available for the black hole to consume. Another proposes that strong magnetic fields in the vicinity of Sagittarius A may be playing a key role influencing the accretion of matter and reducing the overall energy output. Regardless of the exact cause, Sagittarius A's relative quietness presents a unique opportunity for scientists. It allows them to study the fundamental properties of a supermassive black hole without the interference of powerful jets or intense radiation, potentially providing crucial insights into the underlying physics of black hole accretion and behavior. The study of Sagittarius A's unusual quietness, therefore, is not simply a matter of noting a peculiarity. It is a valuable avenue for research, potentially unlocking key insights into the complexities of black hole physics and galactic evolution. This relative calm, however, may be temporary. The Milky Way's central region is a dynamic environment, and future interactions with gas clouds or stars could trigger a significant increase in Sagittarius A's activity. The study of Sagittarius A, therefore, is not only about understanding its current state, but also about predicting its future behavior and its long-term impact on the Milky Way galaxy. Its current quiescence offers a unique window into the workings of a supermassive black hole, but the possibility of future outbursts reminds us of the dynamic nature of these cosmic behemoths and their potential to dramatically shape their galactic surroundings. While Sagittarius A is currently relatively quiet, evidence suggests that it may have been far more active in the past. Imagine a sleeping giant occasionally stirring. That's analogous to Sagittarius A's behavior. Its current quiescence doesn't necessarily imply a history of inactivity. Several lines of evidence point to a more energetic past. Observations of X-ray echoes bouncing off nearby gas clouds suggest that the black hole may have been significantly brighter just a few hundred years ago. These echoes detected by instruments like the Chandra X-ray Observatory represent faint remnants of past radiation, indicating a period of increased activity. Another compelling clue comes from the Fermi bubbles, two enormous lobes of gamma-ray emission, extending far above and below the galactic plane. These massive structures, spanning tens of thousands of light-years, are believed to be the remnants of powerful outflows or jets from the galactic center, possibly linked to a past period of heightened activity from Sagittarius A. The energy required to create these structures is immense, indicating that Sagittarius A might have once been a much more active galactic nucleus, similar to the brilliant quasars seen in other galaxies. This past activity may also have played a significant role in shaping the Milky Way's structure and evolution. Powerful outflows from an active Sagittarius A could have influenced the distribution of gas and dust, impacting star formation and shaping the overall structure of the galactic bulge and halo. While the exact nature and timing of these past energetic events remain uncertain, The evidence strongly suggests that Sagittarius A's current relative quietness is not representative of its entire history, a history which continues to be revealed through ever more sensitive observations and refined theoretical models. These clues from the past are therefore invaluable in piecing together a more complete picture of Sagittarius A's evolution and its profound impact on the Milky Way galaxy. Studying these remnants of past activity therefore provides crucial insights into the long-term behavior of supermassive black holes and their role in shaping the evolution of their host galaxies. The current relatively low activity level of Sagittarius A may simply represent a temporary phase in its long and dynamic history, a phase that offers a unique opportunity to study this cosmic giant in a less turbulent state, but also a phase that emphasizes the need for continued monitoring to better understand its past, present, and future behavior. Supermassive black holes, while often perceived as simply destructive forces, play a surprisingly complex and multifaceted role in the evolution of their host galaxies. Imagine a conductor leading an orchestra. The black hole acts similarly, influencing the dynamics and development of its galactic surroundings. Their immense gravitational pull shapes the orbits of stars and gas clouds, affecting the distribution of matter within the galaxy. However, their influence extends far beyond mere gravitational attraction. Active supermassive black holes, those actively accreting matter, can unleash enormous amounts of energy, driving powerful outflows, jets of plasma and radiation that can extend far beyond the galaxy's boundaries. These outflows, traveling at near light speed, can significantly impact the interstellar medium, heating and pushing gas and dust, influencing star formation rates. In some cases, these outflows can even expel significant amounts of material from the galaxy, potentially quenching star formation altogether. This feedback mechanism, where the black hole's activity influences the conditions for star formation, is a crucial aspect of galaxy evolution. The energy released by active supermassive black holes can also ionize surrounding gas, creating vast regions of ionized gas influencing the chemical composition of the interstellar medium. Furthermore, the gravitational influence of supermassive black holes is thought to play a role in regulating the overall morphology and structure of galaxies. Their presence in galactic centers can help stabilize the distribution of stars and gas, impacting the formation and evolution of spiral arms bars and other large-scale galactic structures. The study of supermassive black holes, therefore, isn't just about understanding these enigmatic objects themselves. It's about understanding their crucial role as drivers of galactic evolution, profoundly shaping the structure and development of galaxies across the cosmos. Their influence, exerted through gravity and powerful outflows, is a fundamental aspect of the universe's largest-scale structures. This intricate interplay between supermassive black holes and their host galaxies highlights the interconnectedness of cosmic structures and the complex feedback mechanisms that shape the universe. Further research into this dynamic relationship promises to provide deeper insights into the evolution of galaxies and the fundamental forces governing the cosmos. Understanding the influence of black holes is therefore not merely an academic pursuit. It is a crucial step toward a more complete understanding of the universe's grand design. A common characteristic of active supermassive black holes is the presence of a bright accretion disk, a swirling vortex of gas and dust spiraling inwards, heated to incredible temperatures by friction and gravity. These disks radiate immense energy, often outshining entire galaxies, making active galactic nuclei some of the brightest objects in the universe. Imagine a drain in a bathtub, the water swirling rapidly before disappearing down the drain. That's somewhat analogous to the accretion disk around a black hole. However, Sagittarius A presents a puzzle. Its accretion disk is surprisingly faint. While some material is undoubtedly falling into the black hole, the amount of radiation emitted is far less than expected based on its mass and the amount of surrounding material. This unexpected faintness has led to intense scrutiny and numerous hypotheses attempting to explain this intriguing discrepancy. One leading theory suggests that Sagittarius A is currently in a state of radiatively inefficient accretion. In this scenario, the infalling matter is too diffuse and spread out to generate the expected levels of radiation. Imagine trying to build a campfire with loosely scattered twigs instead of tightly packed logs. You'll get some heat and light, but far less than if the fuel were densely packed. Similarly, the infalling material around Sagittarius A might be too diffuse to efficiently convert gravitational energy into radiation. Another contributing factor may be the influence of magnetic fields. Strong magnetic fields near the black hole could be redirecting or even repelling some of the infalling matter, preventing it from reaching the inner regions of the accretion disk, where it would generate significant radiation. The relative faintness of Sagittarius A's accretion disk, therefore, is not merely an observational quirk. It's a significant puzzle highlighting our incomplete understanding of black hole accretion and the complex interplay of gravitational and magnetic forces near the event horizon. Further research employing advanced techniques and sensitive instruments is needed to fully understand the nature of Sagittarius A's accretion flow and its unexpectedly dim disk. This faintness, however, doesn't diminish the importance of studying Sagittarius A's accretion flow. Even a relatively dim disk can provide valuable insights into the behavior of matter in extreme gravitational environments, offering clues to the underlying physics and potentially revealing subtle details about the black hole's properties that might otherwise be obscured by intense radiation. The unexpected faintness of Sagittarius A's accretion disk therefore serves as a reminder of the complexities of black hole physics and the many unanswered questions that remain questions that future research will hopefully help address. The unexpectedly faint accretion disk around Sagittarius A suggests a process known as radiatively inefficient accretion flow, RIAF. Unlike the bright, tightly packed disks seen around many active galactic nuclei, RIAF involves a less dense and less organized flow of matter spiraling into the black hole. Imagine a gentle stream of water flowing into a drain compared to a rushing torrent. RIAF is more akin to the gentle stream. In RIAF, the infalling material is less dense and less compact, reducing the friction and consequently the amount of heat generated. This lower density also allows for more efficient escape of energy. Instead of being trapped and converted into radiation, much of the energy is carried away by outflows, making the overall radiation output significantly lower. Several factors could contribute to the RIAF around Sagittarius A. The relatively low density of gas and dust in the Milky Way's central region may provide a limited supply of material for accretion. Additionally, the complex magnetic fields near the black hole might play a significant role. These magnetic fields could act as a kind of barrier or regulator, influencing the flow of matter towards the black hole and reducing the efficiency of accretion. The presence of RIAF around Sagittarius A, therefore, is not merely an observational anomaly, but offers valuable insights into the dynamics of black hole accretion. It suggests that the efficiency of converting gravitational energy into radiation is strongly dependent on the density and structure of the infalling matter and the strength of the magnetic fields present. The study of Sagittarius A's RIAF therefore provides a unique opportunity to study the processes governing black hole accretion under conditions different from those seen in more active galactic nuclei. Further research into this phenomenon could revolutionize our understanding of black holes and their interaction with their surrounding environments. This research will not only enhance our understanding of Sagittarius A, but also provide a broader context for interpreting observations of other black holes, potentially revealing universal principles governing accretion processes across the cosmos. The study of Sagittarius A's radiatively inefficient accretion flow, therefore, is a crucial step toward a more complete and nuanced understanding of black hole physics and their profound impact on the evolution of galaxies. The insights gained from this research could have far-reaching implications shaping our understanding of galactic evolution and the intricate dance between black holes and their host galaxies. This deeper understanding, in turn, will help us interpret observations of other galaxies, potentially revealing universal patterns and processes governing the evolution of black holes and their influence on the cosmos. For decades, Sagittarius A remained an invisible giant, its presence inferred through its gravitational influence on nearby stars and its powerful radio emissions. Visualizing this unseen behemoth presented a formidable challenge requiring a revolutionary approach: the Event Horizon Telescope, EHT. Imagine trying to photograph a firefly from miles away. That's the scale of the challenge in imaging a black hole. The EHT isn't a single telescope, but a global network of radio observatories working together to create a virtual telescope the size of Earth. By synchronizing observations across multiple continents, including observatories in North America, Europe, Asia, and South America, the EHT achieved the unprecedented resolution necessary to image the shadow cast by Sagittarius A's event horizon. This wasn't a simple task. It involved coordinating observations with atomic clock precision, ensuring that the signals from each observatory arrived at the processing center precisely synchronized. The sheer volume of data collected was enormous, requiring specialized high-capacity hard drives to transport the information for processing. The data processing itself was a monumental undertaking, utilizing sophisticated algorithms to stitch together the signals from different observatories, accounting for the Earth's rotation and other sources of interference. In May 2022, the EHT collaboration finally released the first-ever image of Sagittarius A, a blurry but unmistakable ring of light surrounding a dark central region, the black hole's shadow. This groundbreaking image wasn't just a technological marvel, it represented a profound scientific triumph, visually confirming the existence of a supermassive black hole at the heart of our galaxy, and providing a direct test of Einstein's theory of general relativity in one of the universe's most extreme environments. The EHT image of Sagittarius A, therefore, was more than just a picture. It was a landmark achievement representing the culmination of decades of research, technological innovation, and international collaboration, opening a new era in our understanding of black holes and their place in the cosmos. This image, while blurry, provided crucial information about the black hole's size, mass, and the dynamics of its surrounding environment. The observed shadow's size precisely matched theoretical predictions, offering a compelling visual confirmation of Einstein's theory. The asymmetry in the brightness of the ring revealed details about the swirling plasma near the event horizon, providing insights into the complex interplay of gravity and magnetic fields in this extreme environment. The EHT's success in imaging Sagittarius A therefore not only provided a visual testament to the existence of this supermassive black hole, but also marked a pivotal moment in astrophysics, demonstrating the power of international collaboration and technological innovation to unravel the universe's deepest mysteries. The image is a testament to human ingenuity and our relentless pursuit of knowledge, opening a new chapter in our quest to understand black holes and their profound influence on the cosmos. The Event Horizon telescope's image of Sagittarius A revealed not a smooth, symmetrical accretion disk, but a far more chaotic and turbulent structure. Imagine a whirlpool, its waters churning and swirling unpredictably. That's analogous to the turbulent flow of matter around Sagittarius A. Instead of a neatly organized disk, the observations revealed a complex dynamic system where hot gas and plasma swirl and collide, creating a messy and uneven distribution of brightness. This turbulent flow is likely driven by a complex interplay of forces: the immense gravity of the black hole, the influence of magnetic fields, and the chaotic motion of infalling matter. The gas and plasma near the black hole are heated to incredibly high temperatures, emitting radiation across a wide range of wavelengths. However, this emission isn't uniformly distributed. The image revealed bright spots and patches indicative of turbulent regions, where matter is being compressed and heated more intensely. This uneven distribution of brightness suggests a highly dynamic and unstable accretion flow, far from the idealized smooth disk often depicted in theoretical models. The observed structure therefore highlights the limitations of simplified models and the complex reality of matter interacting with a supermassive black hole. The turbulence is likely shaped by powerful magnetic fields threading through the plasma, creating complex patterns and influencing the flow of matter towards the event horizon. These magnetic fields can also generate their own emission, further complicating the overall structure and brightness distribution observed in the EHT image. The chaotic nature of Sagittarius A's accretion flow therefore provides invaluable insights into the behavior of matter in extreme gravitational fields, a domain where our understanding is still evolving. Further study of this turbulent disk using increasingly sophisticated techniques and models promises to deepen our understanding of black hole physics and the dynamics of accretion processes in the universe. This turbulent environment, therefore, is not merely a chaotic backdrop. It's a crucial component of the black hole's interaction with its surroundings, influencing the rate of accretion and the emission of radiation. Understanding the structure and dynamics of this turbulent disk is paramount to unraveling the mysteries of black hole physics and their role in shaping the evolution of galaxies. The intricate interplay of gravity and magnetic fields within this turbulent disk therefore remains a key area of ongoing research, promising to yield further insights into the complex workings of supermassive black holes and their influence on the universe. Even in its relatively quiet state, Sagittarius A occasionally erupts in dramatic bursts of energy known as flares. These flares, observed across various wavelengths, represent sudden and unpredictable increases in brightness, sometimes exceeding the black hole's typical emission by dozens of times. Imagine a sleeping giant occasionally flexing its muscles. These flares are similar brief moments of intense activity. These events are not evenly spaced or tied to any easily discernible pattern. They appear seemingly at random, catching astronomers off guard and triggering intense observation campaigns to gather as much data as possible before the flare subsides. The rapid rise and fall of these flares suggest a compact origin, indicating that the source of the outburst lies very close to the black hole's event horizon, within a region smaller than the distance light travels in a few minutes. Several theories attempt to explain the origin of these flares. One hypothesis involves clumps of gas falling into the black hole. In this scenario, denser pockets of material, perhaps originating from nearby stars or gas clouds, could be caught by the black hole's gravitational pull and spiral inwards, releasing a burst of energy as they are heated to millions of degrees before vanishing beyond the event horizon. Another theory centers on magnetic reconnection events. Black holes can generate and trap incredibly powerful magnetic fields. The sudden reconfiguration or reconnection of these tangled field lines could release a substantial amount of energy in a brief but intense burst of radiation. A third possibility involves the disruption of stars or smaller black holes that stray too close to Sagittarius A. The immense tidal forces near the black hole could rip apart such objects, sending debris spiraling inwards, creating a spectacular flare. Regardless of their precise origin, Sagittarius A's flares provide invaluable opportunities to study the complex physics near the event horizon, offering unique insights into the dynamics of black holes and their interaction with the surrounding environment. The unpredictable nature of these flares therefore makes them all the more intriguing, highlighting the dynamic and still partially mysterious nature of our galaxy's central black hole. The study of these outbursts promises to reveal more about the behavior of matter in extreme gravitational fields, testing the limits of our understanding of both black holes and the wider universe. These sudden bursts of energy, therefore, are not simply random events. They are valuable probes into the extreme physics governing the environment immediately surrounding a supermassive black hole, offering a unique window into a realm we can never directly observe. The unpredictable flares from Sagittarius. While captivating, pose a significant challenge explaining their origin. Several competing hypotheses attempt to account for these sudden bursts of energy, each offering a unique perspective on the complex processes occurring near the black hole's event horizon. One leading theory attributes the flares to clumps of gas falling into the black hole. Imagine dropping pebbles into a still pond. The impact creates ripples. Similarly, denser pockets of gas within the accretion flow could be drawn towards the black hole, heating up intensely and releasing a burst of radiation as they are consumed. The size and density of these clumps would determine the intensity and duration of the resulting flare. Another compelling hypothesis focuses on magnetic reconnection events. Black holes are surrounded by incredibly powerful and tangled magnetic fields. When these field lines suddenly reconnect, a process analogous to solar flares on our Sun, a vast amount of magnetic energy can be released in a brief, intense burst of radiation. This mechanism could explain flares that don't seem to be associated with the infall of significant amounts of matter. A third, less frequent but still plausible scenario involves the disruption of stars or smaller black holes that venture too close to Sagittarius A. The immense tidal forces exerted by the black hole's gravity could rip apart these objects, sending streams of material spiraling inwards and producing a bright flare. Each of these models offers a potential explanation for the observed flares, but currently none can fully account for all observed characteristics. The variety in flare intensities, durations, and spectral properties suggests that multiple mechanisms might be at play. Further research combining detailed observations across multiple wavelengths with sophisticated simulations is crucial to distinguish between these hypotheses and ultimately unravel the mysteries behind Sagittarius A's unpredictable outbursts. The study of these flares, therefore, is not merely an exercise in cataloging events. It's a critical avenue for testing our understanding of black hole physics and the extreme environments that surround them. These intense bursts of energy offer a unique opportunity to probe the physics of extreme gravity and magnetism, pushing the boundaries of our understanding of black holes and their interaction with the surrounding universe. The ongoing study of Sagittarius A's flares therefore promises to reveal new insights into the dynamics of these enigmatic objects and their role in shaping the cosmos. Each new flare provides a fresh opportunity to refine our models and deepen our understanding of these powerful events and their implications for the broader universe. Observing and interpreting the flares from Sagittarius A present a unique set of challenges. These outbursts are unpredictable, appearing without warning, and lasting for only a short duration, requiring astronomers to be constantly vigilant and ready to react quickly when a flare occurs. Imagine trying to photograph a fleeting lightning strike. That's the scale of the challenge. The location of Sagittarius A, deeply embedded within the dense galactic bulge, adds another layer of complexity. The obscuring effects of interstellar dust and the crowded stellar field make it difficult to isolate the black hole's emission from the background light, requiring advanced techniques to filter out unwanted signals and pinpoint the source of the flares. The rapid variability of the flares, their sudden rise and fall in brightness, further complicates observations. To capture the full evolution of a flare, astronomers need to gather data across a wide range of wavelengths, from radio waves to X-rays, requiring coordination between multiple telescopes on the ground and in space. This coordination, involving teams across the globe, necessitates careful synchronization of observations and sophisticated data processing techniques. Analyzing the data obtained during these flares also poses considerable challenges. The complex interplay of gravity and magnetic fields near the event horizon makes it difficult to definitively link observed changes in brightness to specific physical processes. Sophisticated computer simulations and advanced theoretical models are needed to interpret the observations and distinguish between competing hypotheses. The study of Sagittarius A's flares, therefore, is more than just a matter of pointing a telescope and taking a picture. It's a complex and demanding scientific endeavor requiring advanced technology, international collaboration, and innovative data analysis techniques. These challenges, however, highlight the scientific significance of these unpredictable outbursts, providing unique opportunities to probe the extreme physics near a supermassive black hole and push the boundaries of our understanding of the universe. Overcoming these observational hurdles, therefore, is crucial for advancing our understanding of black hole physics and the extreme environments that exist at the centers of galaxies. Each successful observation brings us closer to unraveling the mysteries surrounding these dynamic events and their profound implications for the universe. The insights gained from these challenging observations will undoubtedly shape our understanding of black holes for years to come. The persistent effort to overcome these challenges, therefore, is a testament to the dedication and ingenuity of scientists in their pursuit of knowledge about the universe's most enigmatic objects. In May 2019, Sagittarius A produced a flare of unprecedented intensity, exceeding all previously recorded levels by a significant margin, more than twice its typical maximum brightness. Imagine a volcano suddenly erupting with far greater force than ever before observed. This superflare was a similar unexpected event. This exceptionally bright flare immediately captured the attention of astronomers worldwide, triggering intense observation campaigns using telescopes across the electromagnetic spectrum. The intensity of the 2019 superflare shocked scientists, prompting speculation about its possible causes. Initial hypotheses ranged from the disruption of a nearby star to a massive influx of gas falling into the black hole. The sheer energy released during this event was remarkable, exceeding previous observations by a factor of 2, suggesting that an exceptionally large amount of material was rapidly consumed by Sagittarius A. The event was particularly significant because its intensity and duration provided astronomers with an unprecedented opportunity to study the processes occurring near the black hole's event horizon under extreme conditions. The detailed analysis of data gathered during this event is still ongoing, but early results suggest that it might have been caused by a large clump of gas, or perhaps even a small star falling into the black hole. This superflare therefore offered a rare glimpse into the extreme physics near a supermassive black hole, providing valuable insights into the processes governing accretion and energy release. The 2019 superflare, exceeding all previous records, stands as a reminder of the dynamic nature of supermassive black holes and the many mysteries that remain to be uncovered. Its study offers a unique opportunity to further test existing theories and potentially uncover new physics governing extreme gravitational and magnetic environments. Further analysis of this record-breaking event will likely play a significant role in refining our models of black hole behavior and enhancing our understanding of these powerful and enigmatic cosmic engines. The 2019 Superflare therefore serves as a powerful reminder of the dynamic and often unpredictable nature of supermassive black holes, underscoring the need for continued and vigilant observation of these remarkable cosmic entities. This heightened scrutiny, in turn, promises to yield valuable insights into the fundamental physics governing these extreme environments and the processes that drive these powerful outbursts. The data gathered from this exceptional event, therefore, will undoubtedly contribute significantly to our understanding of black hole behavior and the complex processes occurring near their event horizons. This detailed analysis, in turn, will help refine our models and ultimately deepen our understanding of these remarkable cosmic engines. Gravity isn't the only dominant force shaping the environment near Sagittarius A's event horizon. Incredibly powerful magnetic fields play a crucial and often overlooked role. Imagine an invisible sculptor molding and shaping the flow of matter. That's analogous to the influence of magnetic fields near a black hole. These fields, generated by the swirling plasma and charged particles within the accretion flow, are far stronger than anything encountered on Earth. They thread through the surrounding space, twisting and tangling, creating a complex and dynamic magnetic architecture. The Event Horizon Telescope's observations, particularly the polarized light data, have provided crucial insights into the structure and strength of these magnetic fields. The polarization patterns observed in the EHT image reveal the orientation of the magnetic field lines near the event horizon, suggesting a complex and often chaotic arrangement. These fields don't simply passively exist. They actively interact with the infalling matter, influencing its motion, its heating, and its ultimate fate. Magnetic fields can act as a kind of barrier, redirecting or even repelling some of the infalling gas and plasma before it can reach the black hole's event horizon. This can reduce the efficiency of accretion, potentially explaining Sagittarius A's relatively low level of activity compared to other supermassive black holes. Conversely, when magnetic field lines suddenly reconnect, a process similar to solar flares on our Sun, a substantial amount of magnetic energy can be released in a short, intense burst of radiation, contributing to the flares observed from Sagittarius A. The complex interplay between gravity and magnetic fields near Sagittarius A's event horizon therefore is crucial to understanding the dynamics of the accretion flow, the emission of radiation, and the overall behavior of the black hole. Further research into these magnetic fields using advanced techniques like polarimetry promises to reveal further insights into the extreme physics of this fascinating region and the still largely uncharted territory near the black hole's point of no return. Understanding the role of magnetic fields, therefore, is pivotal to completely understanding the behavior and structure of Sagittarius A. This research, in turn, will not only enhance our understanding of Sagittarius A, but also provide a more complete picture of black hole physics and their influence on the evolution of galaxies. The ongoing investigation into the magnetic fields surrounding Sagittarius A therefore is crucial for advancing our knowledge of black holes and their impact on the universe. These powerful invisible forces are fundamental to understanding the behavior of this cosmic giant and its influence on the Milky Way. The continued study of these fields will undoubtedly reveal further insights into the complex dynamics of supermassive black holes and their role in shaping the cosmos. While the Event Horizon Telescope's image of Sagittarius A provided a groundbreaking visual confirmation of the black hole's presence, analyzing the polarization of the light emitted from its vicinity offers even deeper insights. Imagine looking at a painting through different filters. Each filter reveals different aspects of the artwork. Similarly, analyzing polarized light reveals information about the magnetic fields present near the black hole. Light waves, like electromagnetic waves, can vibrate in many different directions. However, certain physical processes, such as scattering off charged particles or passing through magnetic fields, can cause these vibrations to become aligned, creating polarized light. By analyzing the polarization of the light emitted from the region surrounding Sagittarius, astronomers can gain crucial information about the strength and orientation of the magnetic fields present. The EHT's observations revealed that the light around Sagittarius A is significantly polarized, indicating the presence of strong, organized magnetic fields. These fields are not uniform, but show complex patterns suggesting a turbulent and dynamic magnetic environment near the black hole. This polarized light, therefore, is not simply a byproduct of the black hole's activity. It is a valuable probe, giving astronomers a unique view into the magnetic architecture shaping the accretion flow and influencing the black hole's behavior. The analysis of polarized light is providing critical information about the strength, orientation, and structure of the magnetic fields surrounding Sagittarius A. This information is helping scientists to better understand the role of magnetic fields in the accretion process, the generation of flares, and the overall dynamics of the black hole's environment. Further analysis of polarized light from Sagittarius A therefore promises to unlock even deeper secrets about the extreme physics near the event horizon and refine our understanding of the complex interplay between gravity and magnetism in this unique cosmic environment. The study of polarized light, therefore, is a powerful tool offering a new dimension in our efforts to unlock the universe's most closely guarded secrets. This detailed analysis, in turn, will contribute significantly to our understanding of black hole physics and the extreme environments they create. These insights gained through the study of polarized light are essential for building more accurate and comprehensive models of black hole behavior and their influence on the universe. The ongoing analysis of polarized light from Sagittarius A therefore represents a crucial step in our quest to fully understand these remarkable cosmic objects and their impact on the universe. This deeper understanding, in turn, will help us unravel the mysteries of galactic evolution and the universe's grand design. The continuing study of polarized light from Sagittarius A, therefore, is not merely an exercise in data analysis. It is a fundamental step in our ongoing quest to understand the universe. The intense magnetic fields surrounding Sagittarius A play a crucial role in regulating its activity and shaping its observable characteristics. Imagine a conductor controlling the flow of electricity. Magnetic fields similarly govern the flow of plasma and charged particles near the black hole. These fields, generated by the swirling superheated plasma within the accretion flow, are far stronger than anything we encounter on Earth, creating a complex and dynamic magnetic environment that profoundly influences the black hole's behavior. The strength and configuration of these magnetic fields are not uniform. They twist, tangle, and reconnect, creating regions of enhanced or suppressed activity. In regions where the magnetic field lines are tightly wound, they can exert significant pressure, hindering the inflow of matter onto the black hole and reducing the overall rate of accretion. This can result in a relatively lower level of radiative output, contributing to Sagittarius A's surprisingly low activity compared to other supermassive black holes. Conversely, when magnetic field lines suddenly reconnect, a process analogous to solar flares on the Sun, vast amounts of stored magnetic energy can be released in a short, powerful burst, leading to the observed flares from Sagittarius A. The strength and configuration of the magnetic fields, therefore, are intimately linked to both the black hole's overall activity level and the frequency and intensity of its flares. The study of these magnetic fields, using techniques like polarimetry, which measures the polarization of light to infer magnetic field structure, is providing invaluable insights into the complex interplay between gravity and magnetism. near the event horizon, helping us understand how these forces shape the accretion process, regulate the black hole's energy output, and trigger the occasional spectacular flares. The impact of magnetic fields, therefore, is not merely a secondary effect, but a fundamental aspect of Sagittarius A's behavior and its influence on the surrounding environment. Further research into the magnetic field structure near Sagittarius A is crucial for understanding the dynamics of this unique cosmic environment. This research will not only enhance our understanding of Sagittarius A, but also provide a more complete picture of black hole physics and their influence on the evolution of galaxies. This deeper understanding, in turn, will help us unravel the mysteries of galactic evolution and the universe's grand design. The ongoing study of magnetic fields around Sagittarius A, therefore, is essential for a complete understanding of supermassive black holes and their impact on the universe. This knowledge will undoubtedly shape our understanding of galactic evolution and the universe's grand design for years to come. The continuing investigation into this area, therefore, is of paramount importance for unraveling the universe's most profound mysteries. The mysteries surrounding Sagittarius A are far from solved, and continued research in this area promises to yield even more remarkable discoveries in the years to come. At the heart of every black hole lies a boundary beyond which nothing, not even light, can escape the event horizon. This boundary, a point of no return, is defined by the Schwarzschild radius, a concept first described by German physicist Karl Schwarzschild in 1916. Imagine a bowling ball placed on a trampoline. It creates a dip in the fabric of the trampoline. If you roll a marble nearby, it will curve around the dip. Similarly, massive objects warp the fabric of space-time, bending the path of light and other objects. The Schwarzschild radius represents the distance from a black hole's singularity, its central point of infinite density, beyond which the gravitational pull becomes so strong that nothing can escape. This radius depends solely on the black hole's mass. A more massive black hole has a larger Schwarzschild radius. For Sagittarius A, with its mass of approximately 4 million times that of our Sun, the Schwarzschild radius is roughly 12 million kilometers, a surprisingly small distance on a cosmic scale. This doesn't mean the black hole itself is a physical object with a solid surface. The Schwarzschild radius marks the boundary of the event horizon, the point beyond which the escape velocity exceeds the speed of light. Anything crossing this boundary is inevitably drawn towards the singularity at the black hole's center, lost forever to the observable universe. The Schwarzschild radius, therefore, is not merely a theoretical concept. It's a measurable and observable property of black holes, representing the boundary between the observable universe and the realm of the unknown. The size of the Schwarzschild radius is directly proportional to the mass of the black hole. A larger mass means a larger radius. This radius determines the size of the black hole's shadow, observed by the Event Horizon Telescope. The understanding of the Schwarzschild radius, therefore, is essential for interpreting observations of black holes and for testing our understanding of gravity in one of the universe's most extreme environments. This seemingly simple concept, therefore, is fundamental to our understanding of these enigmatic objects. Further exploration of this concept will undoubtedly continue to refine our understanding of black holes and their place in the universe. The Schwarzschild radius, therefore, is not merely a theoretical construct. It is a tangible marker of a black hole's immense gravitational power and a critical element in our efforts to understand these fascinating objects. Its continued study will undoubtedly reveal further insights into the nature of black holes and the extreme physics governing these remarkable celestial objects. This ongoing exploration, therefore, is crucial for advancing our understanding of these enigmatic objects and their place in the cosmos. The quest to understand the Schwarzschild radius and its implications, therefore, is a journey into the heart of some of the universe's most profound mysteries. This journey, fueled by scientific curiosity and technological innovation, promises to reveal even deeper insights into the workings of the universe. The Schwarzschild radius, that critical boundary marking the event horizon of a black hole, isn't simply a theoretical concept. It's a measurable quantity directly related to the black hole's mass, for Sagittarius. Determining this radius required precise measurements of its mass, a feat accomplished through painstaking observations of stellar orbits near the galactic center. Imagine calculating the weight of an invisible object by observing the motion of objects around it. That's the essence of the process used to determine Sagittarius A's mass and subsequently its Schwarzschild radius. The teams led by Reinhard Genzel and Andrea G.Z., using advanced infrared telescopes and adaptive optics, meticulously tracked the orbits of stars orbiting Sagittarius A for years, measuring their positions with exceptional accuracy. This data, combined with sophisticated computer models that account for the complex gravitational interactions within the crowded galactic center, allowed scientists to calculate the mass of the central object with considerable precision. Once the mass was determined, calculating the Schwarzschild radius was relatively straightforward, using the well-established formula derived from Einstein's theory of general relativity, R-Zafbanursorgation, 2gmc2, where g is the gravitational constant, m is the black hole's mass, and c is the speed of light. For Sagittarius, this calculation yielded a Schwarzschild radius of approximately 12 million kilometers, a surprisingly small distance considering the object's immense mass. This precise measurement, therefore, wasn't simply a confirmation of existing theories. It provided a crucial piece of evidence supporting the interpretation of Sagittarius A as a supermassive black hole. The determination of Sagittarius A's Schwarzschild radius, therefore, is a testament to the precision of modern astronomical techniques and the power of combining sophisticated observations with theoretical models. This precise value, in turn, helps us to better understand the size of the black hole's event horizon, the region from which nothing, not even light, can escape. Knowing this radius provides valuable constraints for theoretical models and informs our interpretations of observations made with instruments like the Event Horizon Telescope. This precise calculation of the Schwarzschild radius, therefore, is a critical step in our ongoing effort to understand these remarkable and enigmatic objects. The continued refinement of this measurement through ever more precise observations and sophisticated modeling will undoubtedly further enhance our understanding of black holes and their role in the universe. This ongoing quest for precision, therefore, is a testament to the power of scientific inquiry and our relentless pursuit of knowledge about the universe. The quest to precisely measure the Schwarzschild radius of Sagittarius A, therefore, is a journey into the heart of one of the universe's most profound mysteries. This journey, driven by human curiosity and technological innovation, continues to reveal the universe's deepest secrets. Although a black hole itself is invisible, its presence can be revealed through its gravitational effects on surrounding matter and light. The Event Horizon Telescope, EHT, didn't directly image Sagittarius A. Instead, it captured the shadow cast by the black hole's event horizon, the point of no return, beyond which nothing, not even light, can escape. Imagine shining a flashlight into a dark room. The light illuminates the objects in the room, but the absence of light behind a solid object creates a shadow. Similarly, the intense gravity of a black hole bends the path of light around it, creating a dark region against a brighter background. This dark region, the black hole's shadow, is slightly larger than the black hole's event horizon itself. The EHT's image of Sagittarius A showed precisely this, a dark central region, the shadow surrounded by a ring of bright emission from superheated gas and plasma orbiting the black hole. The size and shape of this shadow, were consistent with theoretical predictions based on Einstein's theory of general relativity, offering compelling visual confirmation of the black hole's existence and properties. The image revealed a slightly asymmetric shadow, indicating that the matter orbiting Sagittarius A is not uniformly distributed and is likely moving at relativistic speeds. This asymmetry and the brightness of the ring provide invaluable insights into the dynamics of the accretion flow and the magnetic fields present. The EHT image of Sagittarius A's shadow, therefore, is not merely a visual representation. It's a landmark scientific achievement directly confirming the presence of a supermassive black hole and providing crucial data for testing our understanding of gravity in one of the universe's most extreme environments. The image, in its blurry but unmistakable form, represents a profound moment in human understanding, a testament to our technological capabilities and our relentless pursuit of knowledge about the cosmos. This visual confirmation of the black hole's shadow, therefore, is a pivotal step in our ongoing quest to unlock the universe's deepest secrets. The detailed analysis of this shadow, combined with other observations, will undoubtedly continue to refine our understanding of black holes and their profound influence on the universe. This iconic image therefore marks not an end, but a new beginning in our exploration of these enigmatic objects. The quest to understand black holes therefore continues, driven by human curiosity and the relentless pursuit of knowledge. The image of Sagittarius A's shadow therefore represents a pivotal moment in this ongoing journey of discovery. It marks a transition from indirect evidence and theoretical models to direct observation, opening a new era of exploration and discovery. This new era, fueled by technological advancements and international collaboration, promises to unveil even deeper insights into the nature of black holes and their profound impact on the universe. The quest to understand Sagittarius A therefore continues, driven by human curiosity and the relentless pursuit of knowledge. At the heart of every black hole lies a singularity, a point of infinite density, where the known laws of physics break down. Imagine a point where all the universe's mass is compressed into an infinitely small space. That's the concept of a singularity. This isn't simply a region of extremely high density. It's a point where our current understanding of gravity and spacetime fails to provide a coherent description. Einstein's theory of general relativity, while remarkably successful in describing gravity in most situations, predicts the existence of singularities within black holes, but it cannot fully explain what happens at this point. According to general relativity, once matter crosses the event horizon, it inevitably falls towards the singularity, a fate from which there is no escape. However, this prediction presents a fundamental problem. Infinite density is a concept that clashes with other fundamental principles of physics, suggesting that general relativity might not provide a complete description of reality in such extreme conditions. This means that the singularity remains a region beyond our current understanding, highlighting the limitations of our current theoretical models and the need for new physics to explain what happens at this point of infinite density. Quantum mechanics. Our current theory of the very small suggests that it is not possible to precisely define both a particle's position and momentum at the same time. This principle might imply that the singularity, rather than being an infinitely small point, could be a region of extremely high but finite density. However, the specific nature of this region is still a matter of active investigation and significant debate. Some theoretical frameworks, such as loop quantum gravity, attempt to reconcile general relativity with quantum mechanics by proposing that spacetime itself has a granular structure at extremely small scales. These approaches might suggest that the singularity is not a physical point, but rather a consequence of the breakdown of our current understanding of spacetime at extremely high densities. The singularity, therefore, remains a profound enigma representing the ultimate frontier of our understanding of the universe. Continued research exploring the intersection of general relativity and quantum mechanics is crucial for a more complete understanding of black holes and their central singularities. The singularity, therefore, is not just a problem for physicists. It highlights the immense scope of the unknown and the limitless possibilities within the cosmos. The quest to understand the singularity, therefore, is a journey into the heart of some of the universe's most profound mysteries, a journey that will continue to challenge and inspire scientists for generations to come. This pursuit of knowledge, driven by human curiosity and the desire to understand our place in the universe, is a testament to the enduring power of scientific inquiry. It is a journey that reminds us of the vastness of the cosmos and the limitless potential for discovery that lies ahead. The exploration of the singularity, therefore, is a testament to the enduring human spirit of inquiry and our persistent quest to understand the universe. This quest, though challenging, is a defining characteristic of humanity's relationship with the cosmos. The journey to understand Sagittarius A spans decades, involving numerous technological advancements and the collaborative efforts of countless scientists. This wasn't a single eureka moment, but a gradual unveiling, a process of accumulating evidence from various observational techniques. 1930s Carl Jansky's accidental discovery of radio waves emanating from the direction of Sagittarius, marking the dawn of radio astronomy and the first hint of something extraordinary at the galactic center. 1950s Groto Reber's independent confirmation of Jansky's findings and the creation of early radio maps of the galactic center, further solidifying the presence of a powerful radio source. 1970s, the development of more sensitive radio telescopes, which refined the location and characteristics of the radio source, now identified as Sagittarius A, and the naming of the exceptionally compact and intense core as Sagittarius A by astronomer Bruce Ballack and Robert Brown. 1990s, the rise of infrared astronomy using instruments like IRIS and later the Spitzer Space Telescope, which pierced the obscuring dust clouds to reveal the stars and gas clouds within the galactic bulge, and advanced techniques like very long baseline interferometry, VBI, enabling increasingly precise measurements of Sagittarius A's size and position. 1990s, 2000s, Reinhard Genzel and Andrea Gzi's pioneering research tracking the movements of stars near the galactic center, providing the most compelling evidence yet for an extremely massive, unseen object, a supermassive black hole. 2000s, 2010s, continued refinement of infrared and radio astronomy, leading to precise mass estimations of Sagittarius A, confirming its status as a supermassive black hole, and the development of advanced techniques such as adaptive optics to sharpen images and compensate for atmospheric distortion. 2010s, 2020s, the Event Horizon Telescope (EHT) project, a global collaboration involving multiple radio observatories, culminating in the first-ever image of Sagittarius A's shadow, providing direct visual confirmation of the supermassive black hole's existence. This timeline, therefore, highlights the collaborative nature of scientific discovery, the cumulative impact of technological advancements, and the enduring human quest to understand the mysteries of the universe. Each step from accidental discovery to groundbreaking imaging built upon previous work, demonstrating the remarkable power of persistent scientific inquiry. The story of Sagittarius A, therefore, is not just about a single object. It's about the evolution of astronomy itself, a testament to human ingenuity and our relentless pursuit of knowledge. The journey to understand Sagittarius A therefore serves as a powerful illustration of the scientific method in action, highlighting the iterative nature of discovery and the importance of technological advancement in pushing the boundaries of human knowledge. This ongoing quest, therefore, is a testament to the enduring human spirit of inquiry and our persistent desire to understand the universe and our place within it. The story of Sagittarius A, therefore, is far from over. It is a continuing narrative of scientific exploration and discovery, a journey that will undoubtedly reveal even more profound insights into the universe in the years to come. The intense gravity of Sagittarius A not only governs the motion of stars in its vicinity, but also affects the path of light itself, creating a phenomenon known as gravitational lensing. Imagine placing a bowling ball on a stretched rubber sheet. The ball creates a dip, and if you roll marbles nearby, their paths will curve around the dip. Similarly, the immense gravity of Sagittarius A warps the fabric of space-time, bending the paths of light rays passing nearby. This bending of light, predicted by Einstein's theory of general relativity, can have several effects. In some cases, intervening objects between us and Sagittarius A can act as natural lenses, magnifying the light from more distant objects behind them. This micro-lensing effect can make faint, otherwise invisible objects briefly appear brighter, providing a unique opportunity to study them. In other instances, the gravity of Sagittarius A itself can act as a lens, bending and focusing light from stars located behind it. This macro-lensing can cause multiple images of the same star to appear, or can stretch the star's light into arcs. By carefully measuring these distortions, astronomers can gain crucial information about the black hole's mass, its distance, and even the distribution of matter in its immediate vicinity. Gravitational lensing, therefore, is not merely a curiosity. It's a powerful tool for astronomers, enhancing our ability to observe objects that might otherwise be too faint or too distant to detect. In the case of Sagittarius, a lensing effect, though challenging to predict and observe because of the highly dynamic environment, can significantly improve the resolution of observations, allowing astronomers to study details close to the event horizon that would otherwise be inaccessible. The exploitation of gravitational lensing, therefore, is crucial for gaining deeper insights into the properties of Sagittarius A and testing our understanding of gravity under extreme conditions. The use of gravitational lensing techniques, therefore, is a testament to the ingenuity of astronomers in harnessing natural phenomena to enhance our exploration of the cosmos. This technique, therefore, is not just a supplementary tool, it is a vital component of our ongoing quest to understand Sagittarius A and the complexities of black hole physics. The continued refinement of these techniques, combined with increasingly sophisticated models, promises to yield even more profound insights into the nature of black holes and their influence on the universe. Gravitational lensing, therefore, is a testament to the power of observation and the remarkable ways in which nature itself can enhance our understanding of the cosmos. This natural phenomenon, therefore, provides astronomers with a unique and powerful tool for exploring the universe's most enigmatic objects. The continued study of gravitational lensing around Sagittarius A therefore promises to yield even more significant discoveries. This ongoing research, therefore, is a testament to the ingenuity and perseverance of astronomers in their quest to unravel the universe's most profound mysteries. The use of gravitational lensing to study Sagittarius A therefore represents a remarkable example of how astronomers can harness natural phenomena to enhance our understanding of the cosmos. Gravitational lensing. The bending of light by massive objects manifests itself on different scales, each offering unique insights into the universe. Imagine a magnifying glass. It can magnify small objects up close, microlensing or distort, and spread out larger objects at a distance, macrolensing. Similarly, gravitational lensing can occur on both small and large scales, producing distinct observable effects. Microlensing. This effect occurs when a relatively small object, such as a star or a planet, passes between a more distant light source and the observer. The gravity of the intervening object bends the light from the distant source, causing it to appear brighter and sometimes even distorted. Microlensing events involving stars near Sagittarius A can reveal the presence of otherwise invisible objects such as faint stars or planets, which might be difficult to detect through other means. This technique has been used to discover and characterize exoplanets orbiting other stars, and potentially could illuminate other nearby objects within Sagittarius A's vicinity. Macrolensing. On a larger scale, gravitational lensing can occur due to massive structures like galaxies or galaxy clusters. These structures can bend and distort the light from distant sources, creating arcs multiple images of the same object, or even altering the apparent brightness and shapes of galaxies. In the context of Sagittarius, a macrolensing effects caused by the black hole's immense gravity can influence the light from stars located behind it, modifying their apparent positions and intensities. This effect offers astronomers a unique tool for measuring Sagittarius A's mass and probing the distribution of matter in its surrounding environment. Careful measurement of these subtle distortions can reveal detailed information about the gravitational field near the black hole and provide constraints on its properties that might be difficult to determine through other methods. The study of both microlensing and macrolensing events around Sagittarius A therefore provides astronomers with multiple avenues for exploring the black hole's properties and its interaction with its surroundings. The combined use of these techniques is a testament to the ingenuity of astronomers in using the universe's own gravitational lensing to probe some of its deepest mysteries. This dual approach, therefore, is a powerful tool that continues to refine our understanding of black holes and their impact on the universe. The ongoing study of lensing around Sagittarius A therefore promises to reveal deeper insights into the nature of gravity and the workings of the cosmos. This research, therefore, is not only crucial for understanding Sagittarius A, but also for advancing our broader knowledge of gravity and the universe's structure. By combining observations from various techniques, including gravitational lensing, we can construct a more complete and accurate picture of this remarkable object and its surroundings. This integrated approach, therefore, is essential for furthering our understanding of black holes and their influence on the universe. The study of gravitational microlensing and macrolensing around Sagittarius A, therefore, is a crucial aspect of modern astrophysics, pushing the boundaries of our understanding of gravity and the cosmos. This ongoing research, therefore, promises to yield even more profound insights into the nature of black holes and their influence on the universe. The continued exploration of these lensing effects, therefore, is vital for deepening our understanding of gravity and the universe's structure. Observing the galactic center presents a formidable challenge. The Earth's atmosphere distorts incoming starlight, blurring images and hindering precise measurements. Imagine trying to focus a camera through a constantly shifting layer of heat haze. That's analogous to the problem posed by atmospheric turbulence. Before the advent of adaptive optics, ground-based telescopes struggled to produce sharp images of the galactic center, limiting the accuracy of observations and hindering our ability to study the stars orbiting Sagittarius A. Adaptive optics, however, revolutionized ground-based astronomy. This ingenious technology uses a deformable mirror to counteract the distortions caused by atmospheric turbulence. Imagine a mirror that constantly adjusts its shape to compensate for the distortions created by the air. That's the essence of adaptive optics. By precisely measuring the distortions in incoming starlight using a reference source, often a laser guide star, computers can calculate the necessary adjustments to the mirror's surface. The mirror's shape changes hundreds or even thousands of times per second, effectively canceling out the blurring effects of the atmosphere. This technology proved particularly crucial for studying Sagittarius A because the precise tracking of stellar orbits near the black hole required extremely sharp images and accurate measurements of stellar positions. Adaptive optics dramatically improved the resolution of ground-based observations of the galactic center, enabling astronomers to follow the intricate dance of stars orbiting Sagittarius A with unprecedented precision. The use of adaptive optics, therefore, was instrumental in obtaining the precise data needed to calculate the black hole's mass and confirm its nature as a supermassive black hole. Without adaptive optics, much of the groundbreaking research on Sagittarius A would have been impossible, a testament to this technology's transformative impact on our ability to study the universe. The use of adaptive optics therefore highlights the ingenuity of astronomers in overcoming technological limitations to achieve remarkable feats of observation and advance our understanding of the cosmos. The development and refinement of adaptive optics therefore represent a significant advance in our ability to explore the universe. This technology therefore has been instrumental in many astronomical discoveries, and its continued development promises to unlock even more secrets of the cosmos. The application of adaptive optics to the study of Sagittarius A therefore stands as a prime example of how technological innovation pushes the boundaries of astronomical observation. This continuous refinement of observational techniques therefore is crucial for pushing the boundaries of our understanding of the universe. The study of Sagittarius A therefore continues to benefit from these advancements, pushing the limits of our understanding of black holes and the cosmos. This ongoing process of improvement therefore is vital for unlocking the universe's deepest secrets. The use of adaptive optics in the study of Sagittarius A therefore represents a significant step forward in our quest to understand the universe. It is a testament to human ingenuity and our persistent drive to explore the unknown. While standard adaptive optics significantly improve the sharpness of astronomical images by correcting for atmospheric distortions, multi-conjugate adaptive optics. MCAO takes this technology a step further, offering even greater capabilities. Imagine trying to focus a camera through a thick, layered fog. Standard adaptive optics might clear up the nearest layer, but MCAO would address multiple layers simultaneously. Standard adaptive optics systems typically use a single deformable mirror to compensate for atmospheric turbulence. However, atmospheric distortion isn't uniform. It occurs at different altitudes, creating a complex layered effect. MCAO addresses this by employing multiple deformable mirrors, each correcting for turbulence at a specific altitude. This layered approach allows for a broader and more uniform correction across a wider field of view, resulting in sharper images over a larger area of the sky. To achieve this, MCAO systems use multiple guide stars, either natural stars or artificial laser guide stars, to measure the atmospheric distortions at different altitudes. Each guide star provides information about the turbulence in a specific layer, allowing the system to independently adjust each deformable mirror to counteract the distortions at that altitude. This multi-layered correction is particularly beneficial for observing regions like the galactic center, where a wide field of view is required to study the complex interplay of stars and gas clouds surrounding Sagittarius A. The benefits of MCAO are substantial. It significantly enhances the resolution and clarity of images, enabling astronomers to track stellar motions with greater accuracy and study fainter objects previously hidden from view. MCAO systems, therefore, are instrumental in pushing the boundaries of ground-based astronomy, providing sharper images and more precise data for researchers studying objects like Sagittarius A. The use of MCAO, therefore, is not merely an incremental improvement. It's a significant step forward in our ability to observe and understand the universe. This sophisticated technique therefore represents a key advance in observational astronomy and will undoubtedly play an even greater role in future observations of the galactic center and other challenging celestial targets. The ongoing development and refinement of MCAO therefore will continue to push the boundaries of our understanding of the cosmos. The application of MCAO to the study of Sagittarius A therefore exemplifies the power of technological innovation in advancing our understanding of the universe. This continuous drive for improvement in observational techniques therefore is essential for unlocking the universe's deepest secrets. The future of astronomy therefore rests on this ongoing pursuit of technological advancement and innovative observational strategies. The continued development of multi-conjugate adaptive optics, therefore, is a crucial investment in the future of astronomy. It promises to unlock even more profound insights into the workings of the universe and our place within it. This continued investment in technology, therefore, is vital for maintaining humanity's pursuit of knowledge about the cosmos. The ongoing refinement of techniques like multi-conjugate adaptive optics therefore ensures that astronomy will continue to push the boundaries of human understanding for generations to come. The Event Horizon Telescope's EHT groundbreaking image of Sagittarius A wasn't a standalone achievement. It built upon years of development and a crucial precursor, the successful imaging of the supermassive black hole at the center of the galaxy, Messier 87 M87. Imagine scaling a mountain. Conquering a smaller peak first provides invaluable experience and strengthens skills for tackling the larger challenge. Similarly, the M87 image served as a critical test run, refining techniques and building confidence for the more challenging task of imaging Sagittarius A M87, with its mass of approximately 6.5 billion times that of our Sun, presents a larger target in the sky than Sagittarius A. Its greater size made it a relatively easier target for the EHT, even though it's far more distant. The larger size also meant that the material orbiting M87 moved at a slower pace than the material orbiting Sagittarius A, providing a more stable target for observation. The successful imaging of M87, therefore, was a monumental achievement in its own right, demonstrating the feasibility of capturing an image of a black hole's shadow. The process involved coordinating observations from a global network of radio telescopes, synchronizing data with atomic clock precision, and utilizing advanced algorithms to process petabytes of data. The resulting image, a bright ring of emission encircling a dark central region, the black hole's shadow, was stunning, providing the first-ever direct visual evidence of a black hole's event horizon. This success was not just a technological marvel, it was a crucial stepping stone validating the EHT's methodology and paving the way for the even more challenging task of imaging Sagittarius A. The M87 image, therefore, wasn't just a scientific achievement in itself. It was a crucial rehearsal, a demonstration of the EHT's capabilities, providing astronomers with the confidence and experience to successfully tackle the more complex and dynamic environment around Sagittarius A. The experience gained from this endeavor, therefore, was invaluable in the ultimate pursuit of imaging Sagittarius A. The detailed insights from this project, therefore, were invaluable to the success of imaging Sagittarius A. The lessons learned from imaging M87, therefore, were directly applied to the Sagittarius A project, significantly increasing the chances of success. The successful imaging of M87, therefore, stands as a remarkable achievement in its own right and a crucial stepping stone in the quest to understand black holes. It paved the way for the even more challenging but ultimately successful imaging of Sagittarius A, a testament to the power of perseverance and incremental progress in scientific discovery. The experience gained from this endeavor therefore proved invaluable in the subsequent imaging of Sagittarius A, highlighting the importance of incremental progress in scientific discovery. The success in imaging M87, therefore, was not just a singular event, but a crucial step in the ongoing quest to understand these enigmatic objects and their role in shaping the universe. It demonstrated the power of international collaboration and technological innovation in tackling some of the universe's most challenging problems. This success story therefore serves as an inspiring example of human ingenuity and our persistent quest to unravel the universe's deepest mysteries. While the Event Horizon Telescope's EHT success in imaging M87 paved the way for the Sagittarius A image capturing our own galaxy's central black hole proved significantly more challenging. Imagine trying to photograph a hummingbird compared to a slow-moving bird. The hummingbird's rapid movement makes it far more difficult to capture a clear image. Similarly, the dynamic environment around Sagittarius A presented unique and significant obstacles compared to M87. Size and apparent size M87, with its mass of approximately 6.5 billion solar masses, casts a much larger shadow than Sagittarius A, making it a relatively easier target for the EHT, despite being far more distant. Sagittarius A's smaller size combined with its proximity to Earth caused its apparent size in the sky to be far smaller, requiring an extremely high resolution to resolve its features. From our perspective, Sagittarius A appears roughly the size of a donut on the Moon, a minuscule target. Variability. While M87's emission changes on timescales of days to weeks, Sagittarius A's brightness changes rapidly on the order of minutes. This rapid variability is due to the incredibly fast orbital speeds of matter near the event horizon, sometimes completing orbits in just a few minutes. This meant that the EHT had to account for a constantly shifting target during the observation period, making image reconstruction far more challenging. Imagine trying to take a clear picture of a rapidly moving hummingbird. The same applies here, though, on a cosmic scale. Galactic environment. 87 lies outside the crowded center of its galaxy, reducing the impact of intervening dust and gas on the observations. Sagittarius A, however, is deeply embedded within the Milky Way's dense galactic bulge, where interstellar dust and numerous other radio sources cause scattering and interference. This obscuring environment significantly complicated data processing, requiring advanced algorithms to filter out unwanted signals. The combined effects of dust and gas therefore significantly degraded the resolution and clarity of signals coming from Sagittarius A. Observational coordination. Because of Sagittarius A's rapid variability, the EHT observations had to be perfectly synchronized across all participating telescopes, an extraordinarily challenging task given their geographic distribution and the need for perfect weather conditions at each location. Even slight variations in timing could result in inconsistencies in the data, making image reconstruction far more difficult. Overcoming these challenges required significant innovation and ingenuity, new algorithms for data processing, meticulous synchronization protocols, and advanced techniques for dealing with atmospheric interference. The successful imaging of Sagittarius A therefore stands as a testament to human ingenuity and our relentless pursuit of knowledge, showcasing the remarkable capabilities of scientific collaboration and technological advancement in pushing the boundaries of astronomical observation. The effort to image Sagittarius A therefore not only yielded an unprecedented image, but also demonstrates the power and versatility of modern astronomical technologies. The successful imaging of Sagittarius A therefore represents a significant leap forward in our ability to observe and understand the universe's most enigmatic objects. This achievement underscores the power of perseverance, international collaboration, and technological innovation in unraveling the universe's deepest mysteries. The challenges overcome in imaging Sagittarius A therefore highlight the remarkable capabilities of modern astronomy and the enduring human quest to explore the unknown. The successful imaging of Sagittarius A, despite these considerable challenges, underscores the remarkable progress in our ability to observe and understand the universe's most complex phenomena. This achievement therefore marks a significant milestone in our ongoing exploration of the universe's most enigmatic objects. It serves as a testament to the power of human ingenuity and our persistent drive to unravel the universe's deepest mysteries. The challenges encountered in imaging Sagittarius A therefore highlight the complexities of studying black holes and the importance of continued technological innovation and international collaboration. The Event Horizon Telescope's EHT image of Sagittarius A, while a monumental achievement, doesn't provide all the answers. This groundbreaking image confirmed the presence of a supermassive black hole at the center of our galaxy, but it also leaves us with several intriguing unanswered questions. Imagine taking a photograph of a distant city. You might see the overall layout, but miss many details of individual buildings. Similarly, the EHT image, while groundbreaking, reveals only a limited amount of information about Sagittarius A. Spin rate. The EHT image doesn't directly reveal the spin rate of Sagittarius A. Black holes can rotate at various speeds from non-rotating to near the maximum speed allowed by physics. The spin rate influences the black hole's gravitational field, its interaction with surrounding matter, and the formation of any jets or outflows. Determining Sagittarius A's spin rate therefore requires further observations and analysis of data from other wavelengths. Orientation. The orientation of Sagittarius A's spin axis relative to our line of sight remains uncertain. Knowing the tilt of this axis is critical for interpreting the structure of the accretion flow and understanding how matter falls into the black hole. More detailed observations, particularly polarization measurements, are needed to constrain the black hole's orientation. Magnetic field structure. While the EHT image hinted at the presence of magnetic fields, detailed information about their structure and strength is still lacking. Magnetic fields are likely key players in shaping the accretion flow, generating flares, and potentially launching jets. A more complete picture of the magnetic field configuration near Sagittarius A requires further observations using techniques like polarimetry. Accretion flow dynamics. The EHT image provides a snapshot of the accretion flow, but detailed information about its dynamics and evolution remains largely unknown. High-resolution observations and advanced modeling are needed to understand how the gas and plasma move and interact within the accretion flow, explaining features like the observed asymmetry and the origin of flares, singularity, and inner structure. The image reveals only the region around the black hole's event horizon. The singularity itself and the region within the event horizon remains entirely hidden from direct observation. Understanding the singularity and what might happen to matter as it approaches the singularity remains one of the greatest challenges in modern physics. These open questions therefore highlight that the quest to understand supermassive black holes like Sagittarius A is far from complete. The EHT image was a monumental achievement, but it serves as a springboard for even more ambitious research, pushing the boundaries of our understanding of the universe's most mysterious and fascinating objects. The unanswered questions therefore underscore the importance of continued exploration and innovation in astronomy. The pursuit of answers to these questions, therefore, will drive future advancements in observational techniques and theoretical modeling, pushing the boundaries of our understanding of black holes and their role in the cosmos. This ongoing quest for knowledge, therefore, is a testament to the enduring human spirit of inquiry and our persistent drive to explore the universe's deepest mysteries. The image of Sagittarius A, therefore, is not an endpoint, but a pivotal stepping stone on a much longer journey of discovery. It represents a crucial moment in our ongoing quest to understand the universe, highlighting both the remarkable achievements of modern science and the vastness of the mysteries that remain. The unanswered questions surrounding Sagittarius A therefore serve as a powerful reminder of the boundless nature of scientific inquiry and the vastness of the cosmos still waiting to be explored. This ongoing exploration, therefore, is a testament to humanity's enduring curiosity and our relentless pursuit of knowledge. The journey to understand Sagittarius A, therefore, is far from over. It is a testament to the power of human curiosity and the endless quest to uncover the universe's secrets. While the Event Horizon Telescope has provided us with an unprecedented view of the region surrounding Sagittarius A's event horizon, the realm beyond remains shrouded in mystery. The event horizon itself marks the point of no return, the boundary beyond which nothing, not even light, can escape the black hole's gravitational pull. Imagine a doorway leading to an unknown realm. The event horizon acts similarly, marking the boundary between our observable universe and the hidden interior of a black hole. What lies beyond this point is a matter of ongoing theoretical exploration, a realm where our current understanding of physics may not apply. According to classical general relativity, once matter crosses the event horizon, it inexorably falls towards the singularity at the black hole's center. This singularity, a point of infinite density, represents a breakdown in our current physical laws and remains one of the most profound mysteries in physics. However, modern physics suggests that quantum effects might play a significant role near the singularity, potentially altering the predictions of general relativity. Some theoretical frameworks propose that the singularity might not be a point of infinite density, but rather a region of extremely high but finite density. Other speculative models suggest the existence of an inner horizon, a second boundary within the black hole, marking a transition to a different kind of spacetime. Within this inner region, it's theoretically possible for particles, or even light, to follow stable paths, although to an external observer, such paths would remain eternally hidden. Even more radical theories propose the existence of wormholes, hypothetical tunnels connecting different regions of spacetime, or perhaps even different universes. In these speculative scenarios, the interior of a black hole might not be a simple point of collapse, but a complex dynamic region with intricate structures and perhaps even stable orbits under conditions utterly unlike those we experience. While these are speculative possibilities, they highlight the profound mystery that lies beyond the event horizon and underscore the need for further theoretical development and observational breakthroughs to better understand black holes. The exploration beyond the event horizon of Sagittarius A therefore represents one of the most challenging yet potentially rewarding areas of astrophysical research, promising to push the boundaries of our understanding of gravity, spacetime, and the fundamental nature of the universe. This theoretical exploration, therefore, is a testament to the power of imagination and the ongoing quest to understand the universe's most enigmatic structures. It reminds us of the vastness of the unknown and the potential for future discoveries that await. The quest to understand what lies beyond the event horizon, therefore, is a journey into the heart of one of the universe's most profound mysteries, a journey that will continue to challenge and inspire scientists for generations to come. This exploration, driven by both theoretical breakthroughs and technological advancements, pushes the boundaries of human knowledge and our understanding of the universe. The mysteries that lie beyond the event horizon therefore continue to fuel our curiosity and drive our exploration of the cosmos. The ongoing quest to understand these mysteries therefore represents a defining aspect of humanity's relationship with the cosmos. It is a testament to our enduring curiosity and our persistent drive to explore the unknown. While the evidence overwhelmingly supports the interpretation of Sagittarius A as a supermassive black hole, it's crucial to acknowledge that in science, alternative hypotheses must be considered and tested, while the black hole model is currently the most compelling explanation. Let's explore some alternative ideas, however improbable they might currently seem. Imagine a detective investigating a crime. While a primary suspect emerges exploring other possibilities is part of thorough investigation. Similarly, even with strong evidence supporting the black hole hypothesis, considering alternative explanations is essential to rigorous scientific inquiry. Dark matter hypothesis. One alternative, though increasingly unlikely, given the observed compactness of the central mass, involves a dense concentration of dark matter. Dark matter, an invisible form of matter that interacts gravitationally but not through electromagnetic forces, makes up a significant portion of the universe's mass. It's theoretically possible that a massive clump of dark matter could exist at the galactic center, producing the observed gravitational effects on nearby stars. However, current models of dark matter don't suggest that it would collapse into such a compact, dense core, and the observed behavior of stars is more consistent with a black hole's gravitational influence. Boson star hypothesis. Another more exotic proposal involves the concept of a boson star, a hypothetical star composed of bosons, a type of fundamental particle. Under certain conditions, a large accumulation of bosons could collapse into a dense object, producing a gravitational field similar to that of a black hole. However, these objects would lack a true event horizon, unlike black holes, and their behavior might differ subtly from that of a black hole. Currently, there's no strong observational evidence to support this hypothesis for Sagittarius A. Gravastars. Gravastars are a theoretical alternative to black holes proposed as a way to avoid the singularity problem predicted by general relativity. In this hypothesis, instead of collapsing into a singularity, a collapsing star forms a shell of exotic matter, creating a surface that would not have a true event horizon. From a distance, a gravastar's gravitational effects would mimic a black hole, making it observationally indistinguishable. However, there's no direct observational evidence to support the existence of gravastars. Other exotic objects. Other theoretical objects, such as fuzzballs objects proposed within string theory, have been suggested as potential alternatives to black holes. However, these are purely theoretical constructs, and there's currently no strong observational evidence supporting their existence in the galactic center. It's vital to emphasize that the black hole hypothesis remains the most compelling and consistent explanation for the observations of Sagittarius A. The extreme compactness of the central mass, the observed stellar velocities, the radio emissions, and the recently obtained EHT image of its shadow all strongly favor the black hole interpretation. Exploring alternative hypotheses, however, is a crucial part of the scientific process, ensuring that all possibilities are considered and further testing of the black hole hypothesis is guided. The exploration of these alternative theories therefore remains a valuable aspect of the ongoing quest to understand Sagittarius A and the fundamental nature of black holes. This open-minded approach to scientific inquiry, therefore, is essential to advancing our understanding of the universe. The ongoing research, therefore, highlights the power of continuous testing observation and the refinement of theoretical models in furthering our understanding of black holes and the universe. The exploration of these alternative hypotheses therefore underscores the dynamic and ever-evolving nature of scientific understanding. It highlights the importance of maintaining a critical and open-minded approach to scientific inquiry, even when faced with seemingly overwhelming evidence in favor of a particular hypothesis. The consideration of these alternatives, therefore, is not a sign of weakness in the black hole hypothesis, but rather a strength reflecting the rigorous and self-correcting nature of the scientific method. The ongoing exploration of these possibilities therefore underscores the dynamic and ever-evolving nature of our understanding of the universe. It is a testament to the power of scientific inquiry and our persistent quest to uncover the universe's deepest secrets. The openness to alternative explanations, therefore, is a hallmark of scientific progress and a testament to the ever-evolving nature of our understanding of the cosmos. The continued exploration of these possibilities, therefore, is essential for advancing our understanding of the universe and our place within it. Sagittarius A's immense gravity and potential past activity have profoundly shaped the Milky Way's evolution, influencing its structure and development over billions of years. Imagine a sculptor shaping a clay model. Sagittarius A acts similarly, influencing the structure of our galaxy. Its influence is most pronounced in the central region, where its immense gravitational pull has shaped the orbits of stars, creating the dense galactic bulge. The concentration of mass around Sagittarius A likely played a crucial role in the formation of this bulge, drawing in gas, dust, and stars during the Milky Way's early formation and influencing the rate of star formation in this central region. The strong correlation between the mass of a galaxy's central black hole and the mass of its bulge suggests a close relationship in their formation and evolution. Sagittarius A's gravity has also influenced the dynamics of stars and gas clouds within the central region, affecting the overall structure and stability of the Milky Way. The presence of a central supermassive black hole such as Sagittarius A is now understood to be a defining characteristic of most large galaxies, playing a fundamental role in their formation and evolution. If Sagittarius A was significantly more active in the past, as evidenced by the Fermi bubbles, its powerful outflows, jets of particles, and radiation would have dramatically affected the interstellar medium, heating and pushing gas, influencing the rate of star formation, and potentially shaping the distribution of matter within the galactic halo. These powerful outflows might have played a crucial role in regulating star formation in the Milky Way, influencing its chemical evolution and overall morphology. The gravitational influence of Sagittarius A is not limited solely to the central regions. Its presence likely also affects the stability and dynamics of the galactic bar, a long, elongated structure of stars that runs through the Milky Way's central region. This bar is believed to play a significant role in funneling gas towards the galactic center, feeding both star formation and the growth of the central black hole. The interaction between Sagittarius A, the galactic bar, and the surrounding stellar and gaseous environment, therefore, is likely a complex and dynamic process. The ongoing study of Sagittarius A, therefore, is essential for gaining a complete understanding of the Milky Way's evolution and the intricate dance between supermassive black holes and their host galaxies. The continued observation of Sagittarius A, therefore, is a fundamental aspect of understanding the formation and evolution of galaxies across the universe. The study of Sagittarius A, therefore, not only reveals secrets of black holes, but also offers critical insights into the larger-scale structure and evolutionary processes that have shaped the Milky Way and billions of other galaxies across the cosmos. The current relative quiet of Sagittarius A, however, may not always be the case. Future interactions with gas clouds or the eventual collision with the Andromeda Galaxy could trigger periods of increased activity, potentially leading to significant changes in the Milky Way's central region. The understanding of Sagittarius A's role in the Milky Way's evolution, therefore, is an ongoing and crucial aspect of astronomical research. Further study will undoubtedly reveal a richer and more nuanced understanding of this intricate relationship, highlighting the power and profound influence of these cosmic giants. This research, therefore, is not only crucial for understanding our own galaxy, but also for gaining a broader perspective on the evolution of galaxies across the universe. By studying Sagittarius A and its impact on the Milky Way, Therefore, we gain invaluable insights into the fundamental processes that shape the universe. This ongoing investigation, therefore, is a testament to humanity's enduring curiosity and our relentless pursuit of knowledge about the cosmos. The story of Sagittarius A and the Milky Way, therefore, is far from over. It is a continuing narrative of scientific discovery, promising to reveal even more profound insights into the universe in the years to come. The mysteries surrounding Sagittarius A and its influence on the Milky Way therefore continue to inspire and drive our exploration of the cosmos. This ongoing quest, therefore, is a testament to the enduring human spirit of inquiry and our persistent desire to understand the universe and our place within it. The study of Sagittarius A and its impact on the Milky Way, therefore, will continue to shape our understanding of galactic evolution and the universe for generations to come. The Event Horizon Telescope's image of Sagittarius A marks a pivotal moment in our understanding of supermassive black holes and galactic evolution. This remarkable achievement, the culmination of decades of research and technological innovation, not only visually confirmed the presence of a supermassive black hole at the Milky Way's center, but also provided unprecedented insights into its properties, its dynamic environment, and its profound influence on our galaxy's formation and evolution. While many mysteries remain, this groundbreaking image represents a significant leap forward in our quest to understand the universe's most enigmatic objects and the forces shaping the cosmos.